let's check and make sure everything's working fine. Everything is looking good so far. Okay, so yeah, a little early, but I figured I might as well get started. Well, I guess since I'm early, I might as well talk about what happened yesterday, because the original plan was for me to do this yesterday, but I'm glad I made sure to keep Sunday clear, because I kind of knew that the unexpected would happen, because it always does in my case. That's just my life, I suppose. So, yesterday, something I didn't take into account was the fact that I was scheduled for my first COVID shot in the morning, and my usual experience with vaccines is I feel a little bit of soreness, but it's something that I can sort of shrug off. That wasn't the case this time. Maybe my age is just catching up to me, but my arm was sore. It's still sore right now, but better than yesterday. And the other thing that was a new experience for me was a slight fever, slight headache, though that probably had more to do with me only getting like 5 hours of sleep yesterday. So I'm not sure if the headache was more induced by the vaccine or the lack of sleep or a combination of the two, but I'm feeling better today, so here we are. So if you've read the description, then you already know I don't really have a plan for what I want to do this time. I just know that this year I wanted to do things differently from last year, because if I was going to do the same thing I did last year, well, then you could just look at the recordings from last year and there wouldn't be much point to it. So I guess what I'm going to do is just kind of comb through my book here and look for inspiration and talk about anything I feel is worth talking about. I did actually talk to some of my students, and one of them gave me some helpful advice. They suggested I do a sort of pseudo lecture, and I thought about it, and I don't want to reteach you calculus or physics, which we'll be covering after we're done with calculus. I'm going to kind of do the same thing as last year in that regard. I'm not going to do chemistry just like last year, because you have my entire 100-hour AP/general college chemistry course available to you. So, yeah, I'm still going to be doing physics after calculus like I did last year. Pretty much going to be going in the same order as far as subjects are concerned. But I don't want to reteach you what you've already learned over the course of the past year. That being said, different people have different experiences from their teachers, so I do still want to do a sort of conceptual review rather than just working problems, because some teachers might not emphasize the importance of certain ideas as much as others, and even if they do, for example, maybe you've forgotten some of the finer details about limits because it's been almost a year since, well, I'd say more like 8 months since you first learned about limits. So enough time has passed where you might have forgotten certain details. And yeah, that's what I'm going to try and go for. So I'm going to go ahead and look through the book and see where I want to start. I'm probably going to kind of start with a problem and then kind of do my conceptual talk based off of that problem. But yeah, let me look around and see what I want to go over first. Okay, here's something that I want to make sure I clear up, because some teachers have a tendency to do this. I know there are some teachers who tell their students that if the limit of a function is infinity or negative infinity, then they can get away with just saying that the limit does not exist. So let's clear that one up first. I'm going to go ahead and copy a graph I see on one of the problems in my book. The numbers on the graph don't really matter all that much, though I guess we will need to insert some numbers. There's going to be a 2 there. And let's see if 2 is there. That's 1, 3, 4, 5. And I guess I'll have to extend that a bit. Let's see. And then it looks like it goes to -3 on that side. -1, 2, 3. My scaling is already off. My drawings are never to scale unless I say so don't trust the scale of what I draw. I try my best to scale things, but, you know, especially in physics, definitely don't trust the scale with which I draw things in physics. Anyway, let's see what they have here. So at -3, and also at 2 and at 5, 3, 4, 5. I'll add a few more ticks there. Here's what they've got. They've got the graph looks like that over there, and then over here it seems to curve down through 0. And then curves down to infinity when you, well, down to -infinity, I should say, as it gets to 2. And then from 2, looks like it kind of reflects back up. And then after 5, it does something like that. Okay, and it says for the function whose graph is shown, state the following. It wants the limit as x approaches 2. It wants the limit as x approaches 5. I guess we'll call it f of x. And I see this marker is as good as dead, so I'll stop using it in a minute. And it wants limit as x approaches -3 from the left. And the limit as x approaches -3 from the right. And I will also add, they don't have this one, but I will add it, the limit as x approaches -3 without a specified direction of approach. Oh, and I forgot to write the f of x there. Let me go ahead and trash this marker and grab a replacement for it. Just a minute. Yeah, that looks far enough from the other colors. Okay, this works. Let me... Yeah, it's a navy blue, though. Most people will probably say it looks black. As long as it contrasts well with my other colors, that's what I try to go for. If you've seen any of my videos where I actually do stuff on paper, you're already used to how I do things with color. I like to have good contrast between my colors because it helps me kind of section off whatever I'm presenting. Makes it easier for people to spot whatever I'm talking about instead of it all being just one big blur of one color. Anyway, so all of these limits are going to be positive or negative infinity or do not exist. And like I was saying before we started this one, sometimes teachers let you get away with saying the limit does not exist, so you could take the easy route and just say does not exist for all of these, but that's not really going to fly, at least not with me, and probably not with college professors, and I'm pretty sure not with the AP exam. It's just, it's taking the easy way out, and you can offer something more sophisticated. The only way you can say that a limit does not exist is if there is no value being approached from either side. If the two sides that you can approach from don't agree. And we'll see that when we talk about this last one over here, which is meant to illustrate that. Anyway, limit as x approaches 2. So we see at 2, since it's I don't want to call it an unsided limit because that sounds like one-sided and I don't want people to mishear me, so I'll call it a non-sided limit. Whenever you have a non-sided limit, which is what you'll have most of the time, you need to check both sides. You need to check the left, you need to check the right. So if I check from the left, coming in from the left, as I go towards 2 coming in from the left, if I trace out this way, I'm going down towards negative infinity. If I approach 2 from the right, so start somewhere right of 2 and get closer towards 2, I'm also going to negative infinity. Left and right agree, there is a limit. If a non-sided limit is the question that you have to answer, if you have to do a non-sided limit, you have to check both sides. If they approach the same value, that's the limit. If they approach different values, there is no limit. That's basically it. So both sides give you negative infinity. We've got negative infinity as x approaches 2. Okay, what about the limit as x approaches 5? Same sort of deal. You check the left, you check the right. From the left, going towards 5, I'm going up towards infinity. If I come in from the right, also coming towards infinity, so positive infinity it is. Okay, limit as x approaches negative 3 from the left. And before I do that, I guess I'll talk about another common thing that students forget. This negative sign doesn't necessarily mean approaching from negative values, it means approaching from the left. Just something worth emphasizing in case it's been a long time since you've done these. So let's see. As x approaches negative 3 from the left, so start somewhere left of negative 3 and move right towards negative 3, and we're going down, it looks like. So that's going towards negative infinity. Limit as x approaches negative 3 from the right. So if we start just to the right of negative 3 and go towards negative 3, we get closer and closer to negative 3. We go further up, so it looks like we're going towards positive infinity there. And of course this one, which I don't know why they didn't include it in the original problem in the book, but thankfully you have me with the sense to add it in. The limit as x approaches negative 3, non-sided. In this case you check both sides, which we already did because parts C and D made us do it, and we can see it goes to negative infinity on one side, positive infinity on the other side, so the non-sided limit does not exist. So if you're going to write DNE for a limit, you better have 1, a non-sided limit, and 2, you better have the two sides not reaching the same value. And if you have a function that looks like if you have a function with like a restricted domain, like the square root function, for example, right? The square root function looks like that. If I wanted the limit as x approaches 0, non-sided, that doesn't exist because from the left, well, there is no left to approach from. If I wanted to do limit as x approaches 0 of square root of x, then that doesn't exist because while we do have 0 coming in from the right, coming in from the left, you have nothing. There's no function to the left of 0. So you just don't have a left to come from. The limit, I would say the limit as x approaches 0 from the left of the square root of x, I would say that doesn't exist. So that's another thing that you can actually use to check if a non-sided limit doesn't exist. Either its left side and right side limits do exist, but they're different, or one of its sides has a limit that doesn't exist. If the limit doesn't exist on one side, then it doesn't exist on the non-sided version of that limit either. Okay, so there's one concept check out of the way. So far, this is kind of going the way I'm imagining. What else can we do here? Let's look for some more inspiration. Oh, and I keep on shifting the paper out of the way. I'm glad I don't write on the very border of the paper. That way, if I do accidentally shove it out of place, you can still mostly see what I'm doing. But I really do need to keep on checking my screen to make sure that it's in full view. Or maybe what I can do is just like carve out a section in here where the paper would fit nicely inside, and that way I don't ever have to worry about shoving it out of the way. But I don't think I can trust my what's the word I'm looking for? I don't think I'm good enough with my hands. I don't think I'm precise enough with my hands to make that work, especially when you consider that this backboard thing isn't all that thick. Though maybe the solution there is just to get a thicker, I don't even know what this foam board thing is called. I just picked it up at an office supply store. I think it was Staples. Anyway, let me look around and see what else I can go over that I think is of import. For the function g whose graph is given. Oh, I know what I want. Let me see if I can find a problem that illustrates it. Denominators that go to 0 tend to give students trouble, so I want to look for something like that. I see some of what I want over here, but not all of it. Okay, that just means I have to make my own. I worry whenever I have to make up my own math problems on the fly because usually I just kind of pick numbers without thinking, and it turns out to be a problem that is technically doable, but the numbers are so messy and they produce results that just kind of don't feel very clean, so to speak. Okay, let's have a look at this one. So it says the limit as x approaches -6 of 2x plus 12 over the absolute value of x plus 6. Now, some students here will notice that you can factor the 2 out of the numerator, and you get 2 times x plus 6 over the absolute value of x plus 6. And here they feel the temptation to just cancel these out, but it doesn't really work that way. So again, you just follow the same principle as before. You check the left side, you check the right side. Now, one little shortcut that you can take is you know that x plus 6 is always going to be positive, except of course at x equals -6, where it's 0. Everywhere else, you can take for granted it's going to be positive. So really the only thing you want to focus on as x approaches -6 is the sign of the numerator. So let's go ahead and rewrite our limit symbol there. Limit as x approaches -6 of all that. And of course we can factor the 2 out of the limit to get it out of the way if you want. I'm not going to bother doing that. I'm just going to check left and check right. So checking left of -6, and let's see if we can do this mentally instead of looking at a graph. So left of -6 just means less than -6. That means more negative. Be careful about that. -5.9, for example, is not less than -6. It's greater than -6. Something that I'm sure you all know, but it's easy to, kind of in the spur of the moment and under the pressure of being in an exam, you sometimes forget little things like that. So less than -6, say -6.1 or -6.01, it doesn't really matter. The point is, if you plug in something less than -6 in for x here, and you add 6 to it, you still have negative something, no matter how small it is. So we've got, as we approach from the left, we've got 2 times something negative over something positive. So we're going to go towards -infinity from the left. So that's limit as x approaches -6 from the left of, okay, fine. I said I wouldn't do it, but I'm factoring out the 2 now. X plus 6 over absolute value of x plus 6 equals -infinity. And how do we know it's -infinity and not some sort of negative constant? Because the denominator, if you try substituting in the -6, you'd get a 0 in the denominator. So clearly it's headed towards one of the infinities, either positive or negative. So that's how we know it's some sort of infinity. Just the fact that the denominator would become 0 if you straight up plugged in the value being approached. Anyway, 2 times limit as x approaches -6 from the right. If we do x plus 6 over absolute value of x plus 6, then over here we should get positive infinity. If I pick something slightly more than -6, like -5.9 or -5.999 or whatever, then add 6 to it and you get positive point something. So positive something over pretty much 0 is a really, really big positive number, so infinity. And there we go. So from the left it's infinity, from the right, or from the left it's negative infinity, from the right it's positive infinity, approaches two different values from two different sides. This limit, non-sided, does not exist. Okay, and it's pretty much the same for other versions of this. So other variations on this limit, you could have something like, let's say, the limit as x approaches 3 of, let's do x minus 3 over x minus 3 squared. And let's compare it to the limit as x approaches 3 of x minus 3 over x minus 3 cubed, or let's say to the 5th, and see if that changes anything. So let me see. If we approach from the left, sub in something less than 3, so like 2.9. Less than 3 minus 3 is negative, and in the denominator, less than 3 minus 3 is also negative, but a negative squared is a positive, so you have a negative over a positive from the left. So left, we get negative infinity. What about right? If I sub in something a little more than 3, more than 3 minus 3 is positive, over more than 3 minus 3 is positive, and positive squared is positive, so you've got positive over positive, which gives a positive infinity. This doesn't exist. What about this one? So we've got limit as x approaches 3. This time the denominator is to the 5th power. So same approach as before. If I try something to the left of 3, something less than 3, less than 3 minus 3 is negative, over less than 3 minus 3, another negative. A negative to the 5th is still a negative, so negative over negative is positive. From the left we get to positive infinity. What about from the right? From the right, more than 3 minus 3 is positive. More than 3 minus 3 to the 5th is also positive. A positive to the 5th is still positive. So positive over positive, we get positive infinity. So this limit does exist. This one does exist. It's equal to infinity. And maybe you noticed there's a little bit of a shortcut you can take with limits that look like this. There's a little bit of a pattern that emerges. When the difference in the degree of these factors, these identical factors, when the difference in the degree is odd, you're going to approach different infinities from different sides. X minus 3 is, you can think of it as x minus 3 to the 1st power over x minus 3 to the 2nd power. 1 and 2, the difference between 1 and 2 is 1, which is odd. When the difference in degree is odd between the factors, you approach different infinities from different sides, whereas when the difference in degree over here is even, difference between 1 and 5 is 4, when it's even, you approach the same infinities. So that's a little bit of a quick check that you can do to figure out whether or not you should even bother with checking the left and right hand sides. This is more of a shortcut than anything, and my rule for shortcuts is you're allowed to use them if you understand how they work. If you do the work and actually explain to yourself, why does this shortcut work? So, why does this shortcut work? Let's look at what's going on, and then we'll talk about the absolute value case in a second. So, the reason this works is because when I look at x minus 3 squared, or, well, when the degree difference is odd, let's take a look at it more generally. When the difference in degree between the factors in the numerator and denominator is odd, what that means is one of them is even and the other is odd. Okay? Well, what happens when one of them is even? When one of them is even, it's always going to give you a positive whether you approach from the left or the right. The other one, which is odd, will give you a negative on one side and a positive on the other side. And that's all there is to it. One of them is always positive, so it has no effect on which sign of infinity you get. The other will be positive on one side and negative on the other side. So you'll get a negative infinity on one side, a positive infinity on the other side. Sometimes it's the left side that's negative, sometimes it's the right side that's negative. You can figure that out on a case-by-case basis, but that's really all there is to it. That's how it works. Okay, what about when the degree difference is even? There are two scenarios. One is where both the numerator and denominator have odd degrees, which is what I've got here, a 1 and a 5. The other case is when they both have even degrees. When they both have even degrees, like let's say if I did x minus 3 squared over x minus 3 to the 8th, is this shade of yellow even visible? Yeah, you can see it. I guess the angle with which I'm looking at it makes it a bit harder for me to see. I mean, I can see it clearly enough because it's right in front of me. But, you know, it just feels like I could imagine it not being visible. So, if both of the degrees are even, then whether it's from the left or from the right, you're always getting a positive over a positive. That's it. That's all there is to it. It's a positive over a positive. So, in fact, Wait, did I put an equal sign there? What am I doing? That equal sign doesn't go there. It goes there. You get positive over positive whether you approach from the left or from the right. So I would say you always get positive infinity, but hold. Not necessarily the case, because you could have like negative signs outside of this. You could have like a negative outside of here. So I would be careful about assuming it's always going to be positive infinity when the degree difference is even. But at least you know when the degree difference is even, the limit does exist. Whether it's positive or negative infinity, you'd have to look at the other stuff that comes with your with whatever's in your limit. Anyway, that's the even over even degree case. What about the odd over odd degree case? Same thing, really. If you look at the odd degree factors, they will approach one sign from the left and they'll approach the other sign from the right. So the numerator switches signs when you switch from left to right, but so does the denominator. And if both the numerator and denominator signs are switching at the same time, if they both are positive over positive from the left, for example, and on the right they both become negative, well, negative over negative is still positive. So yeah, if they're both switching signs at the same time, the sign of the infinity you get on the right is the same as the one you get on the left. So you're not necessarily going to get positive infinity all the time when the degree difference is even. And I guess an example of that I can give is what if I gave you limit as x approaches, I'll stick with 3 here, of what if I did 3 minus x to the third power over x minus 3 to the, let's say, 7th power. In this case, you would get a negative infinity, I believe. Let's check. So if I pick something less than 3, 3 minus less than 3 is positive, positive cubed is positive, over less than 3 minus 3 is negative, and negative to the 7th is still negative. So positive over negative, yeah, you get negative infinity on the left, and because of the pattern that we can now take advantage of, you know you're still going to get negative on the right. It's just going to be a reversal of the roles. The top will be positive, or no, the top was positive on the left, so the top will be negative on the right, but the bottom will be positive on the right, so negative infinity either way. Okay, so what about this absolute value here? It's to the first power, right? So I have an even power difference here. Does this throw a wrench in our rules? Not quite, because it's a different thing, but an absolute value is effectively the same as an even degree factor. An absolute value is essentially the same in an even degree factor, because it's not about evenness and oddness, it's about whether or not the sign, positive or negative, is switchable. And absolute values have unswitchable signs. Absolute values always give you a positive sign, unless there's a negative in front of it. If there was a negative in front of this, then it would always give you a negative. But the point is, it's the same sign no matter what. Whether it's always negative or always positive, it's the same sign on the left side and the right side. So you could mentally think of this as being a factor with an even exponent if you prefer to just calculate the degree difference and see whether it's odd or even. But really the thing you should be looking for is sign switchability, for lack of a better term. Hopefully that insight was helpful to you. I don't think most calculus teachers would go over that. And that's kind of what I intend to cover in these next couple weeks as we approach AP exams. I want to kind of go over the things that teachers may not necessarily cover, or things that you might have forgotten over time, or just common pitfalls and stuff like that. Okay, what else can I grab from here? What else can I grab from here that might be worth our while? I mean, I see these limits. I don't know if there's anything that interesting about them, but I'll look at them anyway. So one of them says, and these are one-sided limits, so, oh, that's what I should call them. Instead of calling them non-sided limits, I should call them two-sided limits. Oh well. I think I prefer the term non-sided anyway. So we've got, it says the limit as x approaches 0 from the left of 1 over x minus 1 over the absolute value of x. You can think of the 1 in the numerator as having a 0 degree term, right? A constant is a 0th degree polynomial, if you want to think of it like that if you want to kind of follow with the pattern we just talked about. But yeah, so this is, let's see, if we do it from, I can see why they did it from the left, because if you did it non-sided, there wouldn't be a limit just because of the 1 over x alone. The 1 over x alone, I would expect you to know what the graph of 1 over x looks like in general. I would expect you to know that its graph looks like that, and so you should be able to easily tell that around x equals 0, to the left it goes to negative infinity, to the right it goes to positive infinity. So on the 1 over x alone, the non-sided limit does not exist. So that's why they wanted you specifically to do it from the left side. From the left side we have, well, 1 over x goes to negative infinity, and minus 1 over the absolute value of x. Actually, this is starting to look more interesting than I initially thought. 1 over x minus 1 over the absolute value of x. So in that case, because it's an absolute value, you're taking a negative minus a positive copy of itself. So you're basically what you're getting is 2 times whatever negative value you have at the left side of 0 for the 1 over x. I don't know if I'm making any sense here. But yeah, 1 over x from the left is going to be some negative value. And if you subtract a positive from it, it's just going to become even more negative. So yeah, that's going to be negative infinity. It's essentially 2 times 1 over x, where 1 over x is something negative. Okay, so that's from the left. What about from the right? Because that's the other part that they're asking here. Limit as x approaches 0 from the right of 1 over x minus 1 over absolute value of x. Okay, well, from the right, 1 over x is positive, minus 1 over absolute value of x is also positive. So here, 1 over x, because it's positive on the right-hand side of 0, it's the same as 1 over the absolute value of x. If it's already positive, then putting absolute value bars around it doesn't change it. It would be the same as the limit as x approaches 0 from the right of 1 over the absolute value of x minus 1 over the absolute value of x, which is going to be clearly 0. So from the left and from the right, you do still approach different values. So the limit, the non-sided limit as x approaches 0 of 1 over x minus 1 over the absolute value of x still doesn't exist because the left and right sides disagree, but their disagreement isn't that they're approaching opposite infinities. Usually when you get a limit that doesn't exist, more often than not, the case you're going to be presented with is the case where the left side approaches one infinity and the right side approaches the other infinity. But this one's a little different from that, which is nice. It's always good to see something different. But yeah, there we go. Okay, let me check on something real quick. Where do I want to go after this? So I don't think there's a need to review the limit laws. AP Calculus doesn't do the whole epsilon delta business, so we don't have to deal with that mess. Oh, here's one that ties into what we've been talking about. The definition of continuity. The limit as x approaches a value, they call it a in my book, of f of x equals f of a. This is the condition for continuity. This is the condition for continuity. The condition for continuity. If a function is continuous, this must hold, at least at that particular value. If this equation holds at the value a, then the function is continuous at a. It could be discontinuous in other places, but it will be continuous at that specific value a. And how do you prove that something is continuous at a whole range of values? That's a bit more complicated, but you can take advantage of some rules. As a rule, polynomials are continuous everywhere. Well, what textbooks will tell you is that a polynomial is continuous on its domain, but since a polynomial's domain is all real numbers, then saying that it's continuous everywhere is still valid. Okay. Anyway, the definition of continuity, its importance lies in a certain type of problem that we sometimes get. Let me see if I can find one over here. Ah, here we go. So let's get a new sheet out. And let me see what we have. We've got a piecewise function, f of x equals, we've got x squared minus 4 over x minus 2. I should have made this bracket much bigger. And then we've got, let's just extend it a little more. And then we've got a x squared minus bx plus 3. And we've got 2x minus a plus b. I hope my b doesn't look too much like a 6 to you guys. And it says that's for when x is less than 2. That's for when x is between 2 and 3. Whoops. X is between 2 and 3. And that's for when x is greater than or equal to 3. Okay, so that's the function we have, and it's asking us to find the values of a and b that make the function continuous everywhere, which I will just interpret as make it continuous at at 2 and 3, because if there's going to be any discontinuity, that's where it would happen. It would be a jump discontinuity if it happens at either of those points. Or maybe an infinite discontinuity, you never know. So if I let x equal 2, then this branch obviously is going to give me trouble, because when x equals 2, you have a 0 in the denominator. The function wouldn't have a value at x equals 2. That's why it's for x less than 2. And over here, if I let x equal 2, then I'll get something. It's a polynomial, so it'll give me some number. So there is a potential that the value approached as you get closer to 2 from this first part of the piecewise function might disagree with the value you have at the beginning of this second part. So that's what the condition for continuity checks for. So if we want to be continuous at 2, the limit as x approaches 2 of f of x needs to be the same as f of 2. And really, what this means is we have to check for 3 things. With the limit, we have to check for 2 sides, so those are 2 things we need to check. And then, of course, we need f of 2 itself. So let's see. Limit as x approaches 2 from the left. So limit as x approaches 2 from the left is going to be, if we have x squared minus 4 from the left, f of x is x squared minus 4 over x minus 2. If we approach 2 from the left, so if I choose something less than 2, well, the good news is we can factor the numerator. Limit as x approaches 2 from the left of x minus 2 times x plus 2 over x minus 2. We are allowed to cancel x minus 2 over x minus 2 because x minus 2 is not 0, it's almost 0, right? X is approaching 2, it's not at 2. We can't divide by 0, but we can divide by almost 0. We can cancel that out just fine. So we're left with x plus 2, which we can safely substitute the 2 into, and that gives us 2 plus 2 is 4. Okay. What about the limit as x approaches 2 from the right? From the right, f of x is going to be ax squared minus bx plus 3. So limit as x approaches 2 from the right of f of x is going to be ax squared, minus, not plus, minus bx plus 3 is going to be a times 2. We can safely substitute 2 here. It's not going to give us any denominator problems like we had with the left-hand side. We can substitute the 2 in here. We get a times 2 squared, so a times 4 minus b times 2 plus 3. So we get 4a minus 2b plus 3. Okay, and so that's the limit as x approaches 2 needs to equal f of 2. So first of all, for that non-sided limit to exist, the left-hand limit must equal the right-hand limit, so 4 must equal 4a minus 2b plus 3. So this 4 must equal 4a minus 2b plus 3. Otherwise, the limit doesn't exist, and a limit that doesn't exist cannot be equal to a function at a particular x value. So if the limit doesn't exist in the first place, then you don't even need to evaluate f of 2. You already know that your function is not continuous. But it's possible for 4 to equal 4a minus 2b plus 3, so we're still safe. We're still in the clear. So what about f of 2? Well, f of 2 is, what do we get when we plug 2 into f of x? We can't plug it into here because this is for x less than 2, so we can't use x squared minus 4 over x minus 2. So we have to use this one. This one has x greater than or equal to 2, so x equals 2 fits into this second part. And that's actually going to give us 4a minus 2b plus 3 again. So I guess you could write equals 4a minus 2b plus 3 another time, but we've already done that once. It would be redundant to do it again. Usually this is going to be the case for these sorts of problems, is either one of the two limits, either the left-hand side or the right-hand side, is going to exactly match f of whatever number you're trying to test continuity at. So yeah, that's one condition we need to have fulfilled. We also need to be continuous at x equals 3, so we need to show, or we need to pick values for a and b such that the limit as x approaches 3 of f of x equals f of 3. And we'll do something similar to what we already did. Let's see. So if I do the limit from the left, the limit as x approaches 3 from the left is, from the left-hand side, we would use ax squared minus bx plus 3, for which I can just use direct substitution. A times 3 squared is 9a, minus b times 3, so minus 3b. So we've got 9a minus 3b plus 3 from the left. From the right, limit as x approaches 3 from the right for f of x. Well, from the right, f of x follows 2x minus a plus b. So 2x minus a plus b is what we'll put in here. And again, we can use direct substitution. It won't cause any problems. 2 times 3 is 6, and that's all she wrote. 6 minus a plus b. So for the limit as x approaches 3, for this to even exist in the first place, these two have to be equal. And then on top of that, these two equal things have to also be equal to f of 3, and f of 3 just happens to be 2 times 3 minus a plus b, which is the 6 minus a plus b we just got. So that's our second condition. 9a minus 3b plus 3 has to equal 6 minus a and plus b. From there, we have two equations in two unknowns, a and b. I would gather the a's and b's together. You know how to solve a system of linear equations. You don't need me to do that for you, so that's where I will stop with that one. You can find the values of a and b that are needed on your own. Let's see. I guess now's a good time to look at the next chapter, which is derivatives and their applications. Definitely don't forget the limit definition of the derivative. That's going to be of great importance. Do not forget the limit definition of the derivative. Well, there's actually a couple different versions of it, so I think it would be worthwhile to list all of them. So the one that I think is most common, or at least the one I see the most, is, wait, no, not this. What am I doing? Is limit as h approaches 0 of f of x plus h minus f of x over h. That's the one that I see the most often. Another alternative version of this is you can say that the derivative at a specific value. This is just f prime of x in general. But if you wanted f prime of x at a specific value, so f prime of a, then another approach you could take is the limit as x approaches a of f of x minus a minus f of a over x minus a. Let me see, does that make sense? No, that does not make sense. Oh, I know. That minus a doesn't belong there. Okay, let me just rewrite it. Let's scrap this. It's better to just have a fresh start. So f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. You could also do the opposite approach. You could do f of a minus f of x over a minus x. If you reverse the order of subtraction in the numerator, but you also reverse the order of subtraction in the denominator, then you're still getting the same value. You're still getting the same ratio. Reversing the order of subtraction is the same as just multiplying by a negative, and if you do that in the top and the bottom, then you're producing two negatives that cancel out anyway. So yeah. Okay, so those are the main two that you want to be on the lookout for, especially this one. So a lot of times students will get stumped if they see something that looks like this. If they have to evaluate the limit as h approaches 0, and usually they'll mask it. Instead of an h, they'll use some other variable here. They'll do the limit as h approaches 0 of, say, let's say 8 plus h minus, wait, no, not this either. Let me just start on a new page. See, this is what happens when I try to come up with problems on the spot rather than using problems that are already in my book. I come up with things that don't make sense. Limit as h approaches 0 of, let's say we had 2 plus h cubed minus 8 over h. And this one is technically doable using just the traditional approach to doing limits. So if you didn't know any better, you could still FOIL 2 plus h cubed and, you know, eliminate whatever needs to be eliminated. Eventually you'd cancel this h in the denominator and you'd be able to safely substitute 0 in for h, but there is another way if you recognize the pattern. This is that first form of the limit definition of the derivative. It's this is clearly your f of x plus h. Well, I shouldn't say clearly because it's not obvious to everyone until you point it out with an example like this, which is why we're doing this in the first place. This is your f of x plus h, and this is your f of x, except not really because there are no x's in here. So it's not really f of x plus h and f of x, it's more like f of some number plus h, right? X is having some value substituted for it in this case, which can make it harder to realize that this is just the limit definition of the derivative. So what I'm seeing here, the first part I would look at is this f of x plus h part, as I've called it. This is what I would turn my focus to, because this will usually help you figure out what the f of x is in the first place. Something plus h cubed. Okay, something plus h cubed. So f of x plus h equals a number plus h cubed. What if the 2 is the x? Let's say the 2 is the x. Let's say it's x plus h cubed. Does that make sense? That would mean that f of just x without the plus h would be x cubed. So does this make sense if x equals 2 here? If x equals 2, then f of 2 plus h is indeed 2 plus h cubed, and f of 2 is 2 cubed, which is 8. So yeah, it works. So there's a little bit of guessing involved, but it's educated guessing. They usually don't make it too obscure, but they make it obscure enough where they're not just handing you the answer, right? There's a reason I wrote this as 8 instead of 2 cubed. If I wrote it as 2 cubed, that would have made it too obvious. But writing it as 8 kind of further tests you and really kind of separates the students that are paying close attention from the students that are not. So let's see, where do I go with this? So it looks like we're dealing with the function x cubed. So we're looking at the derivative of the function x cubed, specifically at x equals 2. So what this is really is f prime of 2, where f of x equals x cubed. As soon as you realize that, you can take the easy way out. You can do f prime of x is going to be 3x squared. F prime of x is going to be 3x squared. And f prime of 2 then is going to be 3 times 2 squared, which is 12. And that, of course, is going to be much faster than foiling out the 2 plus h cubed. The other reason you're going to want to know this isn't just because it's faster. Sometimes it's vital. Sometimes it's impossible otherwise. What if I gave you limit as h approaches 0 of 2 plus h to the 10 minus 1024 over h? You're not foiling that. You're not foiling 2 plus h to the 10. This one makes it extra clear that foiling is not the way to go. The traditional approach is not the way to go with this one. In this case, well, because it kind of matches the same pattern you see here, I think you can already tell this is the derivative of x to the 10th. f of x equals x to the 10, f of x plus h equals x plus h to the 10, and this is at x equals 2. Does it work for x equals 2? Yeah, 2 plus h to the 10 minus 2 to the 10 is 1024. If you deal with computers enough, you probably know this one, or maybe you played that one game, what's it called? 2048, where you slide like the number tiles. I don't know if you've played that game or not. I've seen people play it. It's interesting, I guess. There was, I think, a video by the YouTube channel Numberphile. File spelled P-H-I-L-E, not F-I-L-E. On Numberphile, I think his name was Brady, he showed that game, 2048, to a bunch of math and physics professors, and none of them liked it. You would think if anyone was going to like that game, it would be them. But no, they're like, there's a pattern to this, and once you figure out the pattern, it's not fun anymore. Ruining games with math. Something that one of my computer science professors got a lot of enjoyment out of. But now I'm going off on unnecessary tangents. Let's look through this one. So this one would be, well, derivative of x to the 10 is 10x to the 9, so it's going to be 10 times, in this case, x equals 2 to the 9. 2 to the 9, well, we know 2 to the 10 is 1024, so 2 to the 9 is going to be, divide that by 2, so 512. So 512 times 10 is 5120. There we go. So yeah, just be able to recognize when this is happening, and I guess I should do one in that other form I showed. Actually, I should also mention a third form that you might end up seeing, which is not too different from that first form I showed you. Instead of f of x plus h minus f of x, you could get f of x minus f of x minus h over h. You might get this instead. Let me check mentally if that makes sense. Yeah, it does. I'm just checking quickly through my mind because the way I remember the definition of the limit isn't pure rote memorization. Did I say definition of the limit? Definition of the derivative. The way I remember the limit definition of the derivative isn't purely through rote memorization. It's more like I reconstruct it from, well, the way it was originally developed. I don't want to really get into that and spend too much time on that. I would hope and assume that your teachers already covered that whenever you first learned how to do derivatives using limits. So yeah, that's another form of f of x plus h minus f of x, and I suppose just looking at the two and comparing them, you can convince yourself that it makes sense that they would both be valid. But anyway, let's try and do another example of these, a hidden derivative problem, if that's what you want to call it, using the using this form. So in that form, I guess we could do something like, I don't want to use a pure power function this time. Let's do limit as x approaches How about limit as x approaches 100 of square root of x minus 10 over x minus 100. Yeah. How about this one? I think this one might actually make it easier to spot what your f of x is because, well, there's your f of... Whoops, no, not that one. There's your f of x right there in the format for it. Right? It's pretty easy to match this to... it's pretty easy to match this to f of x minus f of a over x minus a, because everything is just kind of directly mapped. I don't know if that phrasing even helped it make any more sense, but you know, f of x is clearly just its own thing. It's not mixed in with a plus h that makes it harder to see what the x value is and what the f of x itself is. Because 2 plus h cubed, I mean, you could say that this is x plus h cubed with x equals 2, but maybe it's x plus 1 plus h cubed where x equals 1, right? You don't know. You don't know for sure. You're just making an educated guess and testing it against this. So I would argue because of that, that when you're given these hidden derivatives in this form, it's a little bit easier to identify the function. So we've got our f of x is clearly square root of x. Our f of a is 10. Well, we know f of x is square root of x, so the 10 is square root of 100, which means a, in this case, is 100. And that's your x minus a. That reinforces the idea that a is 100. So yeah, everything matches that format. Everything matches f of x minus f of a over x minus a. So this is indeed a derivative. This is indeed f prime of a. And calculating it as a derivative would definitely be far more efficient than calculating it as a limit. If you do it as a limit, then let's see. Would we have to multiply by conjugates here? Yeah, I suppose we would. We'd have to multiply the top and bottom by square root of x plus 10, and that would help us break open that square root and cancel some stuff out. If you directly substitute 100, you're going to get a 0 in the denominator, which is a sign that you have to do some algebra, and if after doing some algebra you still have a 0 in the denominator, then you do what we did towards the beginning of this, which is check the left side and the right side and see what values it's approaching from either side and if they agree or not. Anyway, derivative of the square root of x at x equals 100. Why not? Let's do it. I might as well caution some people about, well, not caution, but recommend something to people about this. So you've seen the derivative of square root of x enough times that I expect you to immediately be able to do this. I expect you to be able to immediately go 1 over 2 square root of x. because by this point you've been doing calculus for however many months now. Let's see, you started in August or September, depending on what state you live in and which district within that state your school is in. So from there, 3-4 months to the end of the year, and now, so I guess 7 months, maybe 8 months. So yeah, you've been at this for several months now, more than half of a year, and I know you've had plenty of opportunities to do this derivative. You've seen it enough times where I would expect you to be able to immediately just come up with 1 over 2 square root of x. If at this point you're still rewriting it as x to the 1/2 and then doing power rule and going 1/2 x to the negative 1/2 and then rewriting that as 1/2 1 over x to the 1/2 and then rewriting that as 1/2 times 1 over the square root of x, and then finally rewriting that as 1 over 2 square root of x. Going through all those steps is going to take up so much of your time on the test, and at this point I would expect you to be able to just know this. It'll save you a ton of time and a ton of stress. Because it's when you're running out of time that your anxiety levels go up dramatically during a test, and anything you can do to be more efficient will, I guess what I'm trying to say is the effect on your mental state is even more valuable than just the time-saving effect. It's not just about saving time, it's also about saving yourself that added stress. Anyway, that's my little mini, I don't even know what to call it. My mini advice section, I guess? Yeah, we'll call it a little bit of pre-exam advice. Anyway, so yeah, we've got a square root of x function. Its derivative is 1 over 2 times the square root of x. When x equals 10, we've got 1 over 2, or no, when x equals 100, I should say, it's 1 over 2 times the square root of 100, which is 1 over 2 times 10, which is 1 over 20. So yeah, so far this is kind of going the way I wanted. I am working out problems, but as you can see, it's not exclusively about problems, or else we probably would have been like, I don't know, 15 problems deep at this point. Yeah, it's more about the concepts surrounding the problems than the problems themselves. So far, I'm liking how this is shaping up. Okay, so that's limit definition of the derivative, just being mindful of it. You already know your differentiation formulas, your power rule, sum and difference rules, constant multiple rule. Your product and quotient rules are 2 of the bigger ones. Your chain rule. I guess I'll go over a little bit of advice for the product and quotient rules. And the chain rule. So, for those 3 rules, definitely organize your information on your paper. Definitely make sure you stay organized and you will be fine. The reason so many students still manage to screw up using those differentiation rules at this late date in the year is because they try to do it all in their head, and they try to do it in a hurry, and there is an advantage to being able to do some of it in your head, but be aware of your mental limitations is what I would say. That's what I would advise. Be aware of your mental limitations. You don't have to hold it all in your head. The human mind can hold, what was it? I think psychologists said that humans can hold 7 plus or minus 2 variables in their head at the same time. So you can only keep track of at least 5 to at most 9 things in your head all at once. So if you've got too many things going on in your head, write some of it down on paper. There's no shame in writing things down on paper. So with product and quotient rule especially, product rule of course is when you've got f of x times g of x, or to abbreviate it, f times g, the derivative of it is f prime g minus g prime f, fig minus gif, and yes, I'm on team gif, not team gif. So f prime g minus g prime f, just organize your problem. If I had, for example, take the derivative of, x squared times sine of x, then, you can pick one of them to be your f, pick the other one to be your g. So I'll say my f is, what am I doing? My f is x squared, my g is sine of x, my f prime is 2x, and my g prime is sine of x. And this one might be simple enough that you can hold all this in your head, and if you can, great, that'll save you time. And like I just mentioned, saving time is good, not just in terms of the actual time you save, but also in terms of, keeping yourself from panicking during the exam. You definitely don't want to be in that state. I hope by advising you not to get too anxious during the exam, I'm not giving you a reason to get anxious about being anxious. That would be, that would not be good. So yeah, you can do, let's see, f prime g, 2x times sine of x, g prime x, or g prime f, sine of x times x squared, or as I would prefer, wait, no, g prime is not sine of x. What did I do here? G prime is cosine of x. There we go. Anyway, cosine of x times x squared, or as I prefer to write it, x squared times cosine of x. It just feels more organized that way. So yeah, you get 2x sine of x plus, did I put a minus here? I'm making mistakes all over the place, aren't I? It's plus g prime f. So 2x sine of x plus, what was it? X squared cosine of x. So yeah, this one is simple enough where you could do it in your head, where I know some of you do it this way, and I definitely encourage you to do it this way when it's simple enough, where you look at it and you think of the product rule as do the derivative 2 times. The first time you do the derivative of the first part and not the second part, and then the second time you do the derivative of the second part but not the first part. I know some of you mentally think of it that way, which is perfectly valid. It works, but if it gets too ugly, if it gets too messy, write it down. Just write it out. Write it out. When in doubt, write it out. If you get something that looks like, this, like x squared plus 3x minus 2 to the 5th power times e to the sine of x cubed. The derivative of this involves a chain rule. This is too messy to try and do it all in your head. Probably. Maybe some of you are those lucky few that can actually hold the maximum of 9 variables in your head and you have no problem with this. But again, know your own limitations. If you see this and you know that you can't handle it all in your head at once, then write it out. Just write it out. So we would have f is all this, g. Oh, actually, both of these are chain rules, come to think of it. Yeah, both of these involve a chain rule. But yeah, for this one I would highly encourage you take this approach. Right, this is your f, right, this is your g. Find your f prime and g prime individually. Just think of them as separate sub-problems and then go back and refocus on the larger problem after you've done those sub-problems. That's my advice to you when it comes to that. I'm not gonna work this one out, just wanted to illustrate the idea for you. And of course the same goes for the quotient rule and the chain rule. Same idea. When in doubt, write it out. I guess for the chain rule, let me see. Because some people are taught the chain rule differently from others. Some people are taught the chain rule as dy dx equals dy du times du dx, and others are taught the chain rule as the derivative of f of g of x equals f prime of g of x times g prime of x. And some people just think of it as take the derivative of the outside, rewrite the inside times the derivative of the inside. If that doesn't make sense to you, don't worry about it. If it does make sense to you, then that's just the approach you're taking. It's perfectly valid. It's basically what this is saying. But yeah, same idea as with product and quotient rule. Identify your f, identify your g. Your f is going to be the outer function, your g is going to be the inner function. Can be a bit of a challenge sometimes. For this, it's simple enough. The inner function is your x squared plus 3x minus 2. Your outer function is x to the 5th, where the x is replaced with this more complicated thing. But yeah, actually, let's do it based off of this one. So if I had my f of g of x equals x squared plus 3x minus 2 to the 5th, then I would say that g of x equals, and you probably want to start with the g of x, the inner function for chain rule problems. My g of x would be the x squared plus 3 of x, or plus 3x minus 2, and my f of x, well, my f of g of x is g to the 5th, so my f of x is x to the 5th. And there you go. And from there you can find f prime of x and g prime of x and match this format and you're good to go. So when in doubt, write it out. You've done chain rule before, you know how to use it, but some of you may not have developed the habit of just kind of writing it out this way and calculating your f prime and g prime and just kind of doing them off on their own section on paper. So that's what I would encourage you to do when it gets especially messy, too messy to do all in your head. If you take this approach, if your teacher taught it to you this way, then it's not all too different. That would be like saying y equals, let me do it in a different color. That would be like saying y equals all that stuff from before. And you can rewrite that as y equals u to the fifth, where u equals the x squared plus 3x minus 2. And then you can do dy du is 5u to the fourth, and then du dx is, let's see, 2x plus 3. So yeah, you can do this stuff. I'll do it over here since I'm running out of space on the bottom. So from this I can get dy du equals 5u to the fourth, du dx equals 2x plus 3, and then dy du times du dx is 5u to the fourth times 2x plus 3, where you would rewrite 5u to the fourth as 5 and then all that stuff to the fourth. I know some of you have never seen it that way, but yeah, that is another way you can do the chain rule. And actually, I find this a bit more memorable because you can sort of have an intuition about it that helps you remember it. Because if you look at it, it kind of looks like you're multiplying two fractions and the du's are canceling out. Don't say that in front of a math professor or a really, really passionate math teacher. They will grill you for it. These aren't really fractions and we shouldn't really treat them as fractions, but they sometimes do things that fractions do. So, just quietly take advantage of that without exposing yourself to the wrath of the professors, so to speak. Okay, let's have a look at some other stuff here. Let's see what else we can do. So we talked about some differentiation rules. Is there anything I want to say about implicit differentiation? Yes, I do. So a lot of teachers don't give their students a second derivative problem with implicit differentiation, so some students might not have seen something like that before. So let's go ahead and do a second derivative just so we understand how to do it. How about this one? We've got x cubed plus y cubed equals 1, and we want to find y double prime. We want to find y double prime. Okay, so implicit differentiation, we get 3x squared plus 3y squared dy dx equals derivative of 1 is 0. Okay, and this one's easier than the typical ones we get. there's only one dy dx term. Let's subtract 3x squared on both sides. 3y squared dy dx equals negative 3x squared. We can cancel the 3's. Dy dx, whoops, dy dx equals negative x squared over y squared. Okay, how do we take the second derivative? The second derivative, we don't double differentiate this. So if you did 6x plus 6y d squared y dx squared, you'd be wrong. That's not how we take a second derivative in implicit differentiation. The second derivative is the derivative of the first derivative. So what we want to do is differentiate this again with respect to x. Oh, and in case you're wondering why the second derivative is written like this, d squared y over dx squared, and not like this, not dy squared over dx squared. If you're wondering why we do it this way, that's because, I might as well talk about this because, again, a lot of math teachers don't talk about this thing. The notation, where does it come from? You can think of the d over dx as the derivative operator. So if I differentiate something, in this case we're differentiating y with respect to x, then it makes sense to write it as dy dx. You know, you're kind of think of it as multiplying the y into the numerator. What if I'm differentiating twice? So here's the derivative of y, the first derivative, and if I want to take that derivative of y and take the derivative of that, so the second derivative, then there you go. I've got two copies of this d over dx. I don't have two copies of the y. So I would have d squared over dx squared if you think of it as multiplying the two d's and the two dx's. And then you've got the y there. Dy squared over dx squared could mean one of two things. It could mean one of two things. It could either mean dy dx times dy dx, which you might have seen if you've done the arc length formula. Or it could mean the second derivative of y squared. So yeah, that's a little side note on notation there. Anyway, what was I doing? Oh, right. So we were taking the second derivative implicitly. So let's continue that up here. So if I want to take the derivative of this with respect to x now, then I guess I have a quotient rule on my hands. We've got f prime g minus g prime f. I'll keep the negative on the outside. So f prime g minus g prime f over g squared. Okay, g squared is simple enough. That's y squared to the second, so y to the fourth. There we go. Now I don't have to hold it in my head. Okay, f prime g minus g prime f. So derivative of x squared is 2x times just the pure y squared minus g prime f. Derivative of y squared is 2y dy dx. So that's g prime times f, which is the x squared itself. I probably should have written the x squared further to the front, but there you go. That's your second derivative so far. Whoops. No, that's an x, not a y. That's an x. I've already messed this up so badly. Okay, let's clean this up a little bit. So negative 2xy squared minus 2x squared y dy dx over y to the fourth equals your second derivative of y. So this dy dx is simply the negative x squared over y squared that we got earlier. You simply substitute that in, and that's how you get a second derivative in implicit differentiation. That's all there is to it. Some people manage to figure this out on their own in spite of their teachers not teaching it. But if you're not one of those students, well, now you know. If your teacher didn't show you an example of this, or if they did show you but they didn't show you enough and you've forgotten, there's your reminder on how to do a second derivative implicitly. And of course you could continue with this reasoning onto the third and fourth derivatives and so on. So yeah, I would just plug in negative x squared over y squared in here. Negative x squared over y squared goes in there. Let's write it out. I think I can fit it in here, so it would be... Oh, wait. Did I move in that negative sign by accident? No, that negative applies to the whole thing. Yeah, so I'll put parentheses around there. Yeah, I moved it into the numerator by accident. Should be outside of the whole thing, but moving it in is fine with those parentheses. Anyway, negative parentheses 2xy squared. The minus becomes a plus because the dy dx has a negative in it when you substitute, so the negatives cancel, you get a plus. 2x squared times another x squared is 2x to the fourth. And then y over y squared is just 1 over y, so there's that. And then over y to the fourth. There we go, that wasn't too bad. I continue to be amazed at how well this shows up on the screen. It barely looks legible to me with this yellow marker, but I guess the people who make these markers knew what they were doing, because you can buy these colors individually. You don't have to buy the multicolor packs that I do. And if yellow wasn't selling individually, it would mean that it wasn't writing well, and the fact that they continue to sell it means that it sold well enough that they didn't have to stop making them. And if it sold well enough that they didn't have to stop making them, then I guess most people are satisfied with how yellow works. I guess I can say that I'm satisfied because it does at least show up for you guys, but not very satisfied. Like, I would definitely encourage discontinuing this yellow or making it like a darker shade. But yeah, there's implicit differentiation. We're getting close to related rates of change and optimization, and I think I caught earlier a comment Yeah, I noticed. I think the last time I did this last year, I didn't open the live chat, but this year it's open, so I see Ryan is requesting optimization problems, and we are soon approaching that. Let me see. Oh, did I? Huh. Interesting. Yeah, I don't know how other streamers do it, how they manage to focus on what they're doing and also pay attention to the live chat at the same time. Uh, I'm kind of worried about what'll happen if this channel gets big enough where the chat is just kind of scrolling by at rapid speed. I mean, I know there's a slow mode, but still, it's even if you slow it down, that almost makes it worse because you know that there's like a flood of comments coming in after the one that you're taking the time to read, and just the anticipation of that is, I don't know, it's not for me. I think you have to be a special kind of, you have to have your brain wired in a special kind of way, or you're severely burnt out by the end of the stream and you just don't show it to your viewers. But yeah, either you have a special kind of brain structure, or you're just like the rest of us and you get burnt out, but you don't show it and you pretend it's all okay, because we have to raise the stakes. We have to constantly be one-upping the other streamers. We have to sacrifice our mental health in order to look like the, I guess, better alternative to all the other streamers you could be viewing. But yeah, we'll see how chat evolves as this channel grows. Where was I? Oh, right. Related rates of change. Is there anything I wanted to do involving related rates of change? I mean, there is something I want to caution about with related rates of change, which is don't plug in values too early. That's a very common mistake I see students making, even this late in the game. Or maybe especially this late in the game, because that's usually a first semester topic and they haven't really, what's the word I'm looking for? They haven't been practicing it all that much recently. Where is my... No, that's... I could have sworn I was already on the page with related rates of change on it. Okay, there it is. It's such a small section that I keep on accidentally skipping over it as I turn the pages in this book. Let's see. Let's pick a problem that'll help us illustrate the things I want to caution about. So, well, the first thing I would want to caution about is know your geometric formulas. Know your geometry. Know your geometry. I don't care if the exam administrators give you a formula sheet that has all the formulas on it. You should know your geometric formulas. I had classmates in third year college physics who didn't know, couldn't remember the volume and surface area formulas for a sphere. That's embarrassing. It shouldn't be that way. Know your geometry. Volume of a cylinder, volume of a cone, volume of a prism, volume of a pyramid, volume of a cube, I think that's the one that everybody remembers. But I'm sure there's somebody out there who's going to prove me wrong. There's somebody out there who proudly doesn't know the formula for the volume of a cube. But yeah, volumes, areas, all those formulas you should know. The distance formula between 2 points, because sometimes these problems involve analytic geometry, and analytic geometry isn't just some fancy term, it's geometry with, geometry in the Cartesian coordinate system. It's, the distance between 2 points. How do you know that two lines, that two equations are parallel to each other? If I wanted to draw a parallelogram and I was given 4 points and you were asked to determine is it a parallelogram or is it not, the things you would do to check for that, that's all called analytic geometry. And in fact, when I was in college, when I took Calculus 2, I did Calculus 1 in the form of AP Calc AB, but in college I took Calculus 2, and at my university it was called Calculus and Analytic Geometry, because yes, the analytic geometry is a big part of calculus. So yeah, if you were wondering what analytic geometry is, that's what it is. Geometry involving coordinates. Distance formula. Pythagorean theorem is what the distance formula draws from, so definitely got to know your Pythagorean theorem. What else? How you can tell that two lines are parallel to each other or perpendicular to each other. I had a student last week, I think. I had to remind them of the property of the slopes of perpendicular lines. Two lines that are perpendicular to each other, if you multiply their slopes, you get -1. So in other words, if you know the slope of one line and you want to get the slope of a line that you want to be perpendicular to it, then you would do -1 divided by the slope of the line you have, and that would give you the slope of the line that will be perpendicular to it. Negative reciprocal. I know some students don't either don't know that in the first place or don't remember it because they haven't used it in a long time. I was reminded of that last week, and again, that's what this review is all for. To remind you of the things you may have forgotten that you will need. So, know your geometry, your area and volume formulas, and also your analytic geometry as a subset of that. Primarily your distance formula, and maybe in some cases you want the midpoint formula, but the midpoint formula I think most people would remember because it's really intuitive. You add the coordinates and divide by 2. It's literally just finding the halfway point in the x's and the halfway point in the y's, and there you go. Let me see. So picking a problem that we can use to illustrate the thing that I warn about when it comes to substituting. Let's do this one, which says gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? Let's have a look at this. So it's in the shape of a cone. And definitely make sure you draw. A lot of people neglect to draw out the scenario that they're working with. Definitely remember to draw things. Okay, so we have height and we have diameter, or perhaps you want radius instead. Yeah, I'll go with radius. And it told us that the base diameter and height are always equal. So 2r is always equal to h. In other words, h equals 2r, or if you prefer, r equals 1/2 h. You could go either way about it. I prefer this way because if you can reduce the number of fractions in your problem, it's usually easier to deal with mentally. It requires less focus, I find, which is good because it means you have more of your, I guess, focus energy saved for the rest of the problem. So that's one thing it tells us. The other thing it tells us is gravel is being dumped at a rate of 30 cubic feet per minute. So volume is increasing. dV dt, change of volume over change in time, is a constant 30 cubic feet per minute, and it's positive. That's something a lot of people forget. You have to check if the rates they give you in the problem are positive or negative, and you infer that from context. Is the thing increasing or decreasing? You infer from context and also from just common sense understanding of the scenario that they present to you. So we've got gravel being dumped at 30 cubic feet per minute, and it says how fast is the height of the pile increasing when the pile is 10 feet high. So the rate of change of the height, dh dt, they say how fast is it increasing, so we expect something positive, and they want it when the height is 10 feet. So at h equals 10 feet. What a lot of people will do mistakenly is they'll go ahead and plug in 10 for h right away. Don't do that. You don't do that until after you have done all your differentiation. If you do it before you differentiate, then you're not differentiating a variable because you've replaced it with a constant. And if you're differentiating a constant, then you're always getting 0, and you're getting a 0 where you should be getting a non-zero, for lack of a better term. So definitely don't do that. Don't plug this stuff in until after you have differentiated. Do not substitute values. Do not, I will emphasize it in writing, do not substitute values. Until after you differentiate. And will I be able to fit this in? Differentiate. I managed to squeeze it in. Do not substitute values until after you differentiate. I think I've repeated that 3 times now. Probably more. My short-term memory isn't all that good. Some people are surprised by that because they see in my videos how I just pull constants and formulas out of my head like it's nothing. That's long-term memory. My long-term memory is just fine. It's my short-term memory that's a mess. I'm working on it gradually, but it's a race against the clock, I suppose, because I'm pretty sure, according to psychologists, as you age, your short-term memory gets worse, but your long-term memory gets better. But, I'm trying. I'm trying to get better with my short-term memory. It's an uphill climb, but I think it's worth it, so I'm going to keep trying. Anyway, so here's where the importance of knowing your geometry comes in. So we have one formula, but it won't be enough. If I differentiate this, then I get dh dt. If I differentiate implicitly with respect to t, by the way, when you're doing related rates, you're doing implicit differentiation. 2 dr dt. Yeah, there we go. Derivative of h is 1 dh dt. Derivative of 2r is 2 dr dt. It's implicit differentiation, just like we did with the earlier problem. We could have implicitly differentiated this with respect to t. Just because the variable is not in the original equation doesn't mean you can't differentiate with respect to this, with respect to it. If you differentiate x cubed plus y cubed equals 1 with respect to t, you would get 3x squared dx dt plus 3y squared dy dt equals 0. So yeah, this is still implicit differentiation that we're doing here. A lot of people don't notice that, and they tend to think of related rates as its own kind of thing. But it's really just implicit differentiation. It's implicit differentiation with applications. We're applying it to a somewhat realistic scenario. When you're pouring something on flat ground, it does tend to pile up in a cone. It's reminding me of that one game theory video on YouTube about what was it? I think it was about the chicken nugget stacking thing with the nugget character from I think the game was called Kindergarten or something like that, where they talked about whether or not it made sense to cushion a fall with a pile of nuggets. But now I'm going off on tangents again. So dh dt equals 2 dr dt. This is good and all, but how on earth are these rates of change related to dv dt? And now you know why they're called related rates of change, if you didn't know already. So we need something more. And this is where our geometry comes in. As I said before, volume equals 1/3. That's going to be pi r squared h. That's why I chose to have a radius instead of a diameter. 1/3 pi r squared h. The volume of a cone is 1/3 the volume of its, I like to call it its corresponding cylinder. 1/3 the volume of a cylinder with a circular base of the same size. So 1/3 pi r squared h. If I differentiate this with respect to t, I get dv dt equals, product rule, I'm going to factor out the 1/3 pi and do the product rule between r squared and h. So derivative of r squared times h plus r squared times the derivative of h. If you want to do it all in your head, this one is one that I would consider simple enough to do in your head. That's going to be 2r dr dt times h. I'm going to multiply the h before I write the dr dt, just because it looks cleaner that way. At least it does to me. Plus r squared times the derivative of h. So r squared dh dt. Perfect. So we've got... I guess I could distribute the 1/3 pi, or I could... No, I'm going to keep it so that I can divide it over to the other side and just get rid of it entirely. That would be much nicer than distributing it. At least to me it would be. So now, after you have done all your differentiation, you can go ahead and plug in your values. I can plug in 30 cubic feet per minute for dV dt. I guess I'll do that up here. And actually go ahead and do... No, I'll do it one step at a time. 30 equals 1/3 pi times 2rh dr dt plus r squared dh dt. Well, dh dt equals 2 dr dt, so I could replace this dr dt with 1/2 dh dt, right? If I divide both sides of this by 2, then I can say 1/2 dh dt equals dr dt, and I can plug that in for dr dt here. So I could do that. The other thing I could do is not do that and just calculate dr dt from here once I... Well, actually no. I would still have to do that, wouldn't I? Yeah, I have to do this anyway. Okay, not what I was expecting. Because sometimes with scenarios like these, you can like calculate the dh dt and the dr dt separately without having to substitute one in terms of the other. Sometimes you have both options. You can either substitute first and solve for one of them and then solve for the other, and other times, and still also have the option of solving for one and then solving for the other, but this isn't one of those scenarios. So yeah, we have to actually replace dr dt with 1/2 dh dt. Or we could replace dh dt with 2 dr dt, but I don't want to do that because dh dt is what we're solving for. So yeah, I would replace the dr dt with 1/2 dh dt. And what else? Well, I have h is 10 feet. What about r? H is equal to 2r, so if h is 10 feet, r is going to be 5 feet. 10 equals 2 times r, so r is going to be 5 feet at that moment in time. So I think with that we have everything. 1/3 pi times the 2 and the 1/2 dh dt. The 2 and the 1/2 reduce, so that 2 is gone. We've got r, which is 5, and h, which is 10, and dh dt, plus r squared. 5 squared is 25, and dh dt again. Okay, and the rest is just solving for dh dt. You know how to do that. Multiply by 3 to get 90, divide by pi, 90 over pi. I guess I'm working it out anyway. And then 5 times 10 is 50, and 25, so 75 dh dt. Divide by 75, and you get your dh dt specifically at the moment when h equals 10 feet. when h equals 5 feet or 4 feet or 100 feet, you're going to get different dHdt's at different times. And it will come out positive because, yeah, if you divide by 75, I see no way that you would get a negative here, so that also checks out. They did ask how fast is the height increasing, and common sense would suggest that the height has to be increasing, plus they said so in the problem itself. So yeah, everything looks good. Everything seems to be making sense. Linear approximation and differentials. I think I will hold on that for later. Maximum and minimum values, we might as well now get to optimization problems. Because that will also have us covering maximization and minimization anyway. And yeah, I'll go back to linear approximation and differentials and linearization and all that at a later time. Maybe today, maybe on a different day, we'll see. Let me check on something real quick. Okay, that's all looking good. Now then, what do I want to say about optimization problems? What are some things to warn and remind about? Well, I guess kind of the same warnings as the related rates problems. Know your geometry for optimization problems because they often involve geometry. But also, the thing I would add to that is apply common sense restrictions to the domains of your functions. Apply common sense or common knowledge restrictions to your function domains. Apply common sense restrictions to function domains. Also, something that I want to go ahead and state is defining an objective function, because a lot of teachers don't really go out of their way to give this definition, but I think it's helpful because it just makes it easier to communicate about these problems. The objective function, you'll hear this term outside of the context of calculus. The first time I heard of an objective function was in I guess you could call it pre-calculus course, where we were doing optimization using matrix calculations. This was before I took any calculus. There's a way to do it with matrices. I guess that's what they would call finite mathematics, I think, is where they teach you to do this. What was it called? I remember it had a name. I think it was called linear optimization. I think that's what it was called. So yeah, the term objective function is not exclusively a calculus thing. But the objective function is, well, the function that is your objective. That's what it is. It's the function such that it's your objective to maximize or minimize it. The function that you're trying to optimize. The function to be maximized or minimized. Or minimized. The function to be maximized or minimized. Okay. So with that out of the way, let's take a look at a classic problem or two. And actually, there's a subset of these optimization problems that I'd really like to look at because they tend to even throw me for a loop sometimes when I'm not being careful. So yeah, I might spend some considerable time on this. So where do I want to start? Let's start with a classic box. Let's start with a classic box. So we've got a box with a square base and open top. I feel like I did this one last year, so in the interest of not redoing a problem I've already done, let's go for a different one. It says if 1,200 square centimeters of material is available to make a box with a square base and an open top, find the largest possible volume of the box. I feel like I might have done this one too, but you know what? Whatever. I'm not going to go back and check right now. If it's a repeat, it's a repeat. If 1,200 square centimeters of material is available to make a box with a square base and an open top, find the largest possible volume of the box. Oh, okay. So this isn't a cutting problem. So when I first read this, I thought this was one of those problems where you have like a piece of cardboard already and you have to cut parts of it. I definitely want to do one of these, so hold that thought. But that's not what this is. It doesn't say you have a 1,200 square centimeter piece that you cut up and fold to make a box. No, here it says 1,200 square centimeters of material is available, so it's assumed you will use all of it. So that's not what this is, not for this problem. So cross that out mentally. This 1,200 square centimeters, that's the total surface area. I'll call it big S. That's going to be your total surface area. Okay, so we've got a box with a square base and an open top. A square base and an open top. So square base and an open top. I guess I've drawn something that looks cubic, but it's not necessarily a cube. Right? The bottom is a square, but the sides could be rectangles. So something like this with no lid. Okay, if I draw the unfolded version of it, it would look something like this. If I were to unfold it and lay it out, should look like this. Some of you are really good at visualizing these in your head, others not so much. So just like I recommended for the related rates problems, draw, draw, draw. So yeah, that's what it looks like unfolded. Okay, so total surface area is 1200 square centimeters, and our objective function is the volume function. We want to have the largest possible volume with the amount of material we have to work with. Okay, well, I'll call it, what should I call it? I'll call it V of x. I'll call it V of x. That's our objective function. V of x equals what? Well, it would have to be the area of the base times the height. Let's say that the sides of the square base have a length of x. So that's x, and that's also x. And then the height is going to be this when you fold it, right? All of those sides that look like this, all of those are going to be heights when you fold them up. These correspond to this. Whereas this right here is x, this is going to be, I'll call it h. That's an h, that's an h, that's an h, that's an h, a whole bunch of h's. Okay, so we've got x squared is going to be the area of the base, and multiply by the height h, and there you go. V of x is x squared times h. Now, the problem with this is that it's a two-variable function. You cannot differentiate it. Well, I mean, you can if you learn some multivariable calculus, but you're doing single variable calculus, so we need another way. And there is another way. We just need to write another equation. So we can make use of our restriction here. I don't want to use pink. I've used enough of that color already. Let's do green. So surface area. Let's go ahead and rewrite it in terms of all this stuff that we have. So surface area is going to be, well, the area of the square base. So surface area, the 1200 square centimeters, is going to equal the x squared plus these four panels, these four rectangular panels. They could be square for all I know, but let's assume for now that they're rectangular. The areas of each of these rectangles is going to be x times h. Right? This is going to be x times h. That side's going to be x times h. And the other two sides are also going to be x times h. So we've got four sides whose areas are x times h, 4xh. There we go. Let's see. So from this, we can actually rewrite h in terms of x. Because what we can do is we can subtract x squared, so 1200 minus x squared equals 4xh. And we can divide by 4x. So we get 1200 minus x squared over 4x equals h. I think I'd rather simplify this a little further and say h is equal to, let's see, 1200 over 4x, 1204 reduced to 300, and that's 300 over x, or 300 times 1 over x. I think that's the better way of looking at it. Minus x squared over 4x, that's going to be 1/4, and then x squared over x is x. Yeah, this is good enough for now. I can substitute that in for h here, And now my objective function is a single variable function. Now my objective function v of x is x squared times 300 over x minus 1/4 x. Distributing the x squared, I get, well, x squared and x reduced to just x, so I get 300x minus 1/4 x cubed is what I get for my v of x. Let's continue this on another sheet. So v of x equals 300x minus 1/4 x cubed. And whenever you're trying to find a maximum or a minimum of a function, the places you look are where the endpoints of your domain are, and also wherever your derivative does not exist, or wherever your derivative is 0. And there's a reason for that. Let's take a look at a graph of a random function, and let's see what we can get from it. This will be a piecewise function because I kind of want to illustrate multiple things with it. Let's say I have a function that looks like this, shifted absolute value function, and then maybe over here it has an open circle, and then it kind of just curves around a bit. Maybe you have something like this, and then something like that, and maybe it goes off to infinity like that, and maybe over here it just has a fixed endpoint. Okay, so endpoints, places where the derivative doesn't exist, and places where the derivative is 0. Why are those the places worth checking for maximum and minimum values? Endpoints are simple enough. An endpoint is either going to be on the starting end or the finishing end, for lack of a better term. And whenever you're at the end, you're most likely going to either have values below it or above it nearby. If it's this point, for example, with this point, there's only 3 ways you could go. You could go horizontally, where the value doesn't change at all, or you could go up from there, or you could go down from there. Unlikely that you're going to be going horizontally. So it is worth checking, because if it's a point you go down from, then it's some sort of maximum, and if it's a point you go up from, then it's some sort of minimum. So that's why endpoints are worth checking. What about places where the derivative doesn't exist? Here's a place where the derivative doesn't exist because there's no function value there to begin with. It's worth checking because it's a place where the function stops for a minute. It's going up and it stops for a split second, just doesn't go anywhere, and then it goes down. It could have continued going up, which is fine. We didn't say it's guaranteed to have a maximum or a minimum. We just said it's a place worth checking if you're looking for a maximum or a minimum, and this is one such place where that could happen. So yeah, there's a stop, and after that stop you could continue going up, or you could turn and go down. If you turn and go down, as my graph shows here, then you've got a maximum here. You were going up, you paused for a moment, then you went down. You're at some sort of high, so this is a place worth checking. Over here is a place where the derivative doesn't exist. Clearly you can tell by looking at the graph this is some sort of minimum. The derivative doesn't exist because, well, the derivative is a limit, as we emphasized earlier, right? A derivative, f prime of x, equals the limit as h approaches 0 of f of x plus h minus f of x over h. And it's a non-sided limit, which means it has to approach the same value from both sides. From this side, the slope, the derivative, is negative. From this side, the derivative is positive. They don't match. The left-hand limit doesn't match the right-hand limit. The derivative here does not exist, and yet you clearly have a minimum. So places where the derivative doesn't exist are worth checking. Places where the derivative is 0. Here's one such place. No action going on here. Clearly we don't have a maximum or a minimum. You were going down and you continued going down from there. You didn't reach a lowest low or highest high within any sort of neighborhood. But if we look here, here's a place where the derivative is 0. And you do have a minimum. Why is it that having a derivative of 0 indicates that this could happen? Because when your derivative is 0, at the points before and after that, your derivative is going to be non-zero. So it's worth checking, because you could be going down and then up, or up and then down. You could also be going down and then down, as we saw here, but still, you have to check to confirm. So all places where derivatives can be 0 are worth checking, because they're places you can turn down into and up from, or up into and down from, as this next one shows. So yeah, that's the logic behind it. That's the basic idea right there. Okay, so now that that spiel is out of the way, let's go back to our original problem. V of x equals 300x minus 1/4 x cubed. We're trying to optimize this. We're trying to find a maximum volume, is what the problem told us it's looking for. What about our restrictions? There is one common sense restriction that we can place on this function. The volume has to be greater than 0. Right? There's no such thing as negative volume. Well, technically you can also have exactly 0 volume, so v of x has to be greater than or equal to 0. The volume can be 0 if you just keep the material flattened out and don't fold it into a box at all. So you can technically have a volume of 0, but the volume has to be positive, and also the dimensions of the volume, the x, the side lengths, have to be greater than or equal to 0. So this is the more important restriction here, the restrictions on x. X has to be greater than or equal to 0, but other than that, the sky is the limit. You could make something light years long but super, super thin and still have a surface area of 1,200 square centimeters. Tough to imagine, but it's technically possible. So yeah, that's the only endpoint we need to consider. We've got a left endpoint, very much like what I have in this example graph. So that's a place worth checking. Well, actually, not really, because we already know when x is 0, the volume is 0, and that's definitely not the maximum. So maybe not worth checking so much after all. Other than that, this is a polynomial. So it's going to be continuous and differentiable everywhere. It's going to be continuous and differentiable everywhere. So I lost my train of thought here. What was I going to say? it's continuous and differentiable everywhere, so we don't have to worry about points of discontinuity or points where the derivative doesn't exist. So those are out. All we have left to look for are points with horizontal tangents, points where the derivative is 0. So if we set v prime of x to 0, let's figure out where this happens. First of all, let's find v prime of x. V prime of x equals 300 minus, let's see, 3/4 x squared. If we set that equal to 0, we see that 300 equals 3/4 x squared if you add it to the other side. Divide both sides by 3, and you get 100. So 100 equals 1/4 x squared. Multiply by 4, 400 equals x squared. And oh so conveniently, the square root of 400 is 20. So x equals plus or minus 20. We can eliminate minus 20 because we already said x can't be negative. Right? This is the common sense restriction that we have. So x is positive 20. That's the only place where a maximum or a minimum could occur. So do we have a maximum or a minimum? The problem told us to maximize the volume, but how do we know that at x equals 20 we're actually getting a maximum and not a minimum? Because we already know what the minimum volume is. The minimum volume would be 0. So any other volume has to be a maximum. Or that's not what I should be saying. Any other critical value should give us a maximum because the absolute minimum we already know is 0. The only other thing we can find is the absolute maximum. And there's only one optimal volume. There can only be one optimal volume. There can only be one maximum volume, so it is the absolute maximum. It's not just a relative maximum. That's, again, just something you can reach through common sense reasoning. Anyway, at x equals 20, if we go ahead and plug it in, v of 20 is... oh, and this is another thing I should warn about with optimization problems. Be very careful when reading the problem. Does it ask for the optimal value, or does it ask for the optimizing value? Do you need to plug back into your objective function to figure out its maximum or minimum value, its optimal value? Or is the problem asking you what length and width and height does the box need to have in order to maximize the volume? Those are two very different questions. You might be tempted to give this as your answer, but if it's asking for the dimensions, then, well, one of your answers is 20 and the other answer is the height, which we can calculate from this now that we know x is 20. So yeah, v of 20, 300, I don't even know why I'm bothering with this at this point. You know how to multiply and all that, but we've already made it this far. We might as well finish what we started. 6,000 minus 1/4 of 20 cubed. Well, 1/4 of one of the 20s is 5 times the other two 20s will give us 400. So that's 2,000. 6,000 minus 2,000 is 4,000 cubic centimeters, right? We were working in centimeters here. As for the optimizing height, if that's what it's asking for, optimizing side length for the square bottom is 20 centimeters. And optimizing height is going to be... Actually, rather than use this, I think it would be easier to use v equals x squared h. Yeah, I'm going to do that. Since I have this, I might as well use it. But normally, if you're being asked for the optimizing values, you wouldn't calculate this to begin with. So this alternative is available to me because I chose to calculate both the optimal and optimizing values, but normally you'd be stuck using this. Poor you. So 4,000 equals x squared, which is 20 squared, times height. Divide by 20 squared, which is 400. 4,000 over 400 is 10 centimeters. And there we go. So that's one optimization problem out of the way. Oh, and I guess one more thing. If you're really hung up on the idea that we can just assume that 20 centimeters, x of 20 centimeters, gives us the maximum volume and not a minimum. If you're really hung up on it, you can always just do the number line check. If you take v prime of x, where was it? Oh, wait, I wrote it on this page, didn't I? 300 minus 3/4 x squared. 300 minus 3/4 x squared. If you do, I like to do the number line method. If you don't like it, then you can use your own method if you like. So hard limit at x equals 0, and then at x equals 20 is where we have a0. This is out of the domain, so no need to consider that part of the number line. Let's see. So yeah, you could just test a value before 20 and after 0, and then another value you could test after 20 and see if you get positives or negatives. So we've got, if I test, for example, 1, 300 minus 3/4 times 1 squared is clearly positive. So you're going to have positive values to the left of 20. To the right of 20, you're going to have, I would assume, negative values. Let's pick something like 100 to make it simple. 100 squared is 10,000 minus 3/4 times 10,000 is, well, a very big negative, big enough that adding 300 to it doesn't change the fact that it's negative overall. So yeah, you've got positive derivative, then 0 derivative, then negative derivative. That means it's going up, pauses for a split second, and goes down. So yes, it is definitely a maximum. So if you are really in doubt, you can always double check that. And also, not just if you're in doubt, sometimes you might get an objective function where the derivative has multiple zeros, in which case you have to test which one is the absolute maximum or minimum. So yeah, you'll still want to remember that you can do this, especially for those scenarios. But for the most part, you can pretty much assume if you only get one maximum or minimum, it'll be what you need. If the problem is asking you to minimize, it'll be a minimum. If the problem is asking you to maximize, it'll be a maximum, because the problem wouldn't make sense if it was the opposite of what you needed. If this was a minimization problem, it wouldn't make sense to begin with. If we were looking for a minimum and we found this, which is a maximum, that wouldn't make sense to begin with. What's the minimum volume you can make with 1,200 square centimeters of material? I mean, that's easy. Just don't use the material at all, or don't fold it at all, and you can get a volume of 0. That's not an interesting problem. So by its very nature, the kinds of things that we would want to optimize, the things that we would even think about optimizing in the first place, they kind of force the, I guess, design of the problem to be such that whatever optimizing value you get, you'll get what the problem is asking for, because the problem just would be too silly if it was asking for the opposite thing. Like, you would easily spot if you were, if you weren't mentally checked out while reading the problem, if you were actually paying attention while reading the problem, you'd easily spot a logical inconsistency of them asking for a minimum when it doesn't make sense, or asking for a maximum where it doesn't make sense. I hope that made sense. Pun partially intended. Well, I don't know if that really counts as a pun, but you know what I mean. Anyway, let's look for the other thing that I want to remind of. What was it? We wanted to do a cutting problem. A cut and then fold problem. Let's see if I can find one of those. Okay, here we have one. So we've got a box with an open top. So open top box again. A box with an open top is to be constructed from a square piece of cardboard, 3 feet wide, by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume that such a box can have. Again, objective function is volume. We are maximizing it because it wouldn't make sense to minimize it. So we've got a square piece of cardboard. And it's 3 feet on a side. So its side lengths are 3 feet. And you want to cut into it. You want to cut into it a bunch of corners. And once you've cut those corners, you're going to end up with something looking like this. Which you can fold along the dotted lines, and it will fold into something looking like this. So let's see. Domain restrictions. I'm going to say that the length of the cut is X. I'm going to say that this length of the cut here is X, which means this is X. It means that this is X. All of these rectangle sides are going to have a length of x along the short side. And I'm going to say that x has to be, well, greater than 0, obviously. But less than what? There is a maximum x, after which point this problem doesn't make any sense at all. X cannot be 1.5 feet. Actually, I'd rather convert the feet to inches, because whatever x is going to be, it's going to be smaller than 3 feet, and if we're working with fractions of a foot, I might as well work in inches. So I'm going to rewrite the 3 feet as 36 inches. And yeah, x of 18 inches is too much. If you're cutting 18 inches on this side and 18 inches on this side, then you've cut the whole side off. There's no rectangle left to fold up. So x is between 0 and 18 inches. So that's our domain restriction. Those are our, I guess you could call them, endpoints. Yeah, open endpoints. And we are looking for v of x, which is going to be, this time, what's it going to be? Well, the base is still a square. We need to get its side length. For now, I'll call it s. So side length squared times height. What's the height? Well, this s translates to this right here, right? And then when you fold these flaps up, the x's along their short ends, that's this right here. That's x. That's your x. So s squared times the height, in this case is x, gives you your volume. Of course, we want to rewrite s in terms of x or x in terms of s. What was it asking us for? Find the largest volume. So the optimal value, not the optimizing values. So we can either rewrite x in terms of s or s in terms of x. We can either make this purely v of x or purely v of s. It doesn't really matter. But yeah, we need to find some other relationship between x and s. So let's go back to this and see what the side length is. So side length can be rewritten in terms of x because this right here used to be the 3 feet until we trimmed it down, right? This was the 3 feet, the 18 inches. But then you removed x from it over here, and you removed x from it over here. You can say the same to this side, right? It's 18 inches, but you remove x from it this way and another x from it this way. So it looks like our side length is 18 minus 2x. 18 minus 2x. I'll rewrite it here for clarity. S equals 18 minus 2x in inches. So I can rewrite v of x as 18 minus 2x quantity squared times x. Okay, I can easily FOIL this. So we've got 18 squared is 324, if my mental math is right, minus 36 times 2, so 72x plus 4x squared times x. Let me double check 18 squared first. Okay, yeah, it is 324. Okay, perfect. And of course I can distribute the x, and I've got 324x minus 72x squared plus 4x cubed. All right. So there's v of x written purely as a function of x. Now we can differentiate it. So we can do, well, this one's not too hard to differentiate. So we've got v prime of x equals 324 minus 144x plus 12x squared, which is going to be set equal to 0. We don't need to check the endpoints 0 and 18 because we already know we're not going to get the optimal values there, right? With x equals 0, you get no volume, and with x equals 18, you get no volume because the sides get completely cut off and you have nothing left to fold, so you'd have no height. You'd just have a smaller piece of square cardboard. So we don't have to check those. We only need to check places where the derivative is 0. There are no places where the derivative doesn't exist because this is a polynomial, and for polynomials the derivative always exists everywhere on its domain. So yeah, we can just, first off, I'm going to rewrite this as 12x squared minus 144x plus 324, just to make it easier for myself to look at. Let's factor out the 12. So 12 times, that's going to be x squared minus 12x plus, let's see, 324. Even without a calculator, I know it's 18 times 18, which is 6 times 3 times 6 times 3. And 6 times 3 times 6 times 3, well, we've got 6 times 3 contains a 6 times 2 in it, right? So it's 6 times 2 plus 6 times 1. What am I even doing? No. Here's how I want to do it. I was making it even more complicated than necessary. 18 times 18 equals, I'll write one of the 18s as 6 times 3 and the other as 2 times 9. There we go. And then the 6 times 2, that's a 12 I can take out. So if you're factoring out the 12, then you're left with a 3 times 9, which is 27. It looks like it's more complicated than long division, but trust me, with practice, doing this mentally is way faster than long division. Anyway, we want that to be equal to 0. Now this should be, I hope, factorable. Otherwise, we've got to use the quadratic formula, which at least it gives you an answer, but it's not really fun to do. Let's see. They multiply to 27 and give negative 12. Negative 3 and negative 9. Yep, that does it. Okay, and both of those work within our restriction, so x equals 3 and x equals 9 are both values to consider. 3 inches and 9 inches, both worth considering. Okay, so we have to actually check both of these now to see which one is higher. So let's plug in 3 and plug in 9 and see what happens. So I guess I would plug it into here. I think it would be easier in this version, actually. Yeah, let's do it in this version. This will probably be easier. If I do 3, 18 minus... Oh, this is why 9... This is why 9 is... We can eliminate 9 off the bat, because I already see it. 18 minus 2 times 9 is 0. Wait. That doesn't... Oh! I messed up. Okay, this wasn't 18 inches, this was 36 inches. Right, it was the 3 feet. Ah. Okay, then... Let me see. If I want to recover from this, we've got, that's going to be 36 minus 2x squared. So it's not going to be 324, it's going to be 4 times that. So I'm just going to say times 4, and then times 4 again there, and then times 4 again there, and times 4 again there. Oh, and the 72 would have to also be doubled, right? Yeah, the 72 would also have to be doubled. Yeah, so that's going to be times 2 times 2. So that's going to be 288, not 144. Oh, goodness. Yeah, I'm better off just starting over. Okay, well, that happens sometimes. So there you have it. It happens even to people with lots and lots of experience. V of x equals 36 minus 2x quantity squared times x. So we get, I'm just going to write it as 36 squared, not even going to touch it, minus 2 times 36 is 72, and then double that, so 144x plus 4x squared all times x, which is, and I'm going to rearrange it, 4x cubed, so I'm writing that first, minus 144x squared, plus, I'm just going to keep it written as 36 squared times x. Okay, and if I differentiate, v prime of x equals, let's do it in, why not green again? $12x squared minus, I'm just going to write it as 2 times 144 so that I can reuse some of the math from earlier, plus 36 squared. Okay, and if I set that equal to 0, and I want to factor out a 12, then factoring out 12 means this will be x squared, this will be, factoring out 12 from 144 gives a 12, times the 2 is 24, so minus 24x plus 36 squared, so that's 3 times 12 times 3 times 12 again. Factoring out a 12 from it leaves us with 3 times 12, 9 times 12, which is 108. You can also think of it as 36 times 3, which is 30 times 3 plus 6 times 3. There are many ways you can mentally get 108 without resorting to a calculator. This is a problem that is totally fair game for the non-calculator section of the AP exam. Actually, I should probably keep the 108 written as 3 times 3 times 12, or even 9 times 12. But, you know, it's whatever. Let's go ahead and see if we can factor this. So it's 12 times x. Looks like we're going to get double negatives. Let's see, 108. So 9 and 12 won't work. Those add up to 21. So that's not going to work. So 9 times 12 doesn't work. What about 18 and 6? Yeah, that works. 18 and 6 works because 9 times 12 can be rewritten as 18 times 6. Multiply the 9 by the 2 and take that 2 out of the 12. Yeah, that works. 6 and 18. Okay, and this gives us x equals 6 or x equals 18. We can eliminate x equals 18 because, well, it's part of our restrictions from earlier, right? If you're cutting that much, you're cutting too much. So even if you didn't place that restriction in the beginning, when you got these two answers, you would have tested them both, and you actually, if you plug in 18 into your v of x function, yeah, if you plug in 18 into your v of x function, you get 0 volume. So even if you weren't applying common sense, I suppose you'd still be safe, but I would recommend trying to think through your common sense restrictions before you start working out the problem, because maybe on the next problem you won't get so lucky. So yeah, x equals 6 is the optimizing value. X equals 6 inches is where you get the maximum volume. And what is the maximum volume? V of 6 equals 36 minus 2 times 6, so 36 minus 12, which is 24 squared, times 6. Let's see, 24 squared times 6. Is there an easier way to do this? 24 squared is 12 times 2 squared, which is 12 squared, 144, times 2 squared, which is 4, times 6. Oh, it's 24 cubed. Wait, no it's not. No it's not. What am I saying? Okay, so this one I would probably turn to the calculator or just leave it as is. But that's in cubic inches. I mean, you can work this out just doing the long form multiplication if you absolutely had to. Or actually, no, you don't even need to resort to that, do you? 4 times 6 is 24. 24 times 144 is 24 times 100, which is 2400, plus 24 times 40, and 24 times 4, which isn't too hard to do because, well, let's do 24 times 4 first. That's not too bad. That's 96. It's 4 off from 25 times 4, which we all know is 100. So, yeah, 96. And then this is going to be 960. So, 2400 plus 960 is 3360. And then plus that 96 gives us 3456. 3456. So yeah, still totally doable without a calculator. And not just doable, there is a way to do it quickly. I think this is definitely more efficient than just your standard multiplication. But then again, maybe some of you use the standard multiplication method a lot faster than I do. Okay, more with optimization problems. This is one that I tend to get confused with a lot myself. Even when I know to look out for it, I still tend to screw up here, where they don't want you to find necessarily where they don't really want you to find a number. So let me see if I can find one of these. Where can I find one of these? I know there was one. I could have sworn it was on that page. Oh, there it is. I think I found it. Okay, it says find the dimensions of the isosceles triangle of largest area that can be inscribed in a circle of radius r. So, in a circle with a radius of r, find the dimensions of the isosceles triangle of largest area that can be inscribed in that circle. So if I were to inscribe an isosceles triangle, let me actually use a lighter color like green here. So I'll just draw a random isosceles triangle. Well, I guess, yeah, to make that actually be an isosceles triangle, I would have to do this. At least this time I'm trying to draw to scale. So yeah, those two sides are going to have to be the same. The third side could be the same, or it could not be. My intuition tells me that the ideal isosceles triangle is going to be an equilateral triangle anyway, but we can't assume that yet. So that's what we have to work with. So find the dimensions of the isosceles triangle of largest area that can be inscribed in a circle of radius r. So we want to maximize the area of the triangle. That's our objective function, and I guess they want it to be a function of r. A of r equals something, and we're trying to maximize it. Okay, so the hard part here is you tend to think of r as a variable, but it's not. The r here is not a variable. The r is a constant. It's a stand-in for a constant value. If it makes it easier for you, replace it with a constant. Replace it with a 4 or a 5 or a 10 or whatever you like, because that's the issue with these, is you easily mistake this for a variable. It's a constant. That being said, let's see what we have to work with. So this isosceles triangle, no matter how you place it, its tip, where the two equal sides are, the vertex where its two equal sides are, and actually all of its vertices, are a distance of r from the center. So that's the first thing we can take advantage of. That's an r, that's an r, that's an r. All of these are equal. Okay, perfect. Now where do we want to go from here? So area of a triangle is 1/2 base times height, right? So we need to rewrite base and height both in terms of, well, actually no. Oh, hold on. I'm already screwing up, aren't I? Area is not a function of r. See, this is what I mean. Even I get mixed up on these. So I want area either as a function of base or as a function of height. Let's say we want it as a function of height. It doesn't really matter as long as we can reduce it down to a single variable. Okay, what is the height and what is the length of the base? That's the question at hand. That's what we have to work with. Or would it make more sense to calculate the area by adding these 3 sub-areas? I don't think so, honestly. I think it would be easier to find some expression for the height here. Let me redraw just the triangle. It's not going to look exactly the same, but something that's close enough. Okay, so its height is that right there. Part of its height is r. So maybe I should use a separate color for this. So here's, I guess, the point that used to be the center of the circle. So that's the part of it that's not r. We'll figure out a way to deal with that later. But part of its height is this r. Those are also r's. Part of its height is r. The rest of its height is this. And another thing we can assume is that this line over here, well, the height of an isosceles triangle is an angle bisector. That's something you learn in geometry. It's also a bisector of the opposite segment of the opposite side. So this line right here, it divides these into 2 equal angles. It also divides these over here into 2 equal sides. Let me use a double, I don't even know what those marks are called, a double tick, I guess. I should figure out what the names of those marks are. Maybe it's something I'll look up later if I remember. I probably won't remember. Again, short-term memory and all that. I mean, I have half an instinct to just Google it now while I still have the thought, but it's not worth it. Okay, let's see. So that's what we have to work with. That line is an angle bisector, and it's also a bisector of that side. I guess, can I come up with a name? Oh, wait. I already do have a name for this, right? We called it the base over here, right? We called this the base. So we do have a name for this. This is 1/2 of b. Okay, perfect. This is actually perfect. Now I can do Pythagorean theorem to get this navy blue line, or what you might consider to be black, depending on the lighting, and also whether or not you may be colorblind. If you are colorblind, I hope my color contrast is good enough for you. I don't know if I'm doing a good job, but I try to pick colors that contrast with each other well enough, so hopefully I'm being helpful. If not, maybe you could give me tips, tell me like which colors I've used that worked well for you, and over time I can just kind of start memorizing what works. Might be difficult because of all the different types of color blindness. I don't know if they conflict with each other, but now I'm going off on another tangent. Let's get back to the problem. So that is 1/2 b, that is r, so this remaining part of the height, so h equals r plus the remaining part, which is, let's see, r is the hypotenuse of this triangle. Let me shade it. So that triangle right there, it has a hypotenuse of r. One of its legs is that, which we're trying to solve for, and the other leg is 1/2 the base. So it's going to be square root of r squared minus the square of 1/2 b. So 1/2 b all squared equals the square root of r squared minus 1/4 b squared. Yeah, there we go. So height is equal to r, this part, plus this darker part, which is the square root of r squared minus 1/4 b squared. Okay, b is variable, r is constant. It helps with these problems to remind yourself what's a constant and what's not. Okay, where do I want to go from here? Well, now that I have h in terms of b, I guess the area of our triangle can now be written. And I guess it's going to be a function of b rather than a function of h. Let's go ahead and do it. So area of our inscribed triangle as a function of b is going to be 1/2 b times r plus the square root of r squared minus 1/4 b squared. Okay, and taking the derivative of this, oh boy, it's going to be quite the mess. And I'd rather just say you know how to do this and just be done with it. But again, keeping track of what's constant and what's not is so important here. So I feel obligated to actually finish this one. Let's distribute the b. Or should I do... No, let's distribute the b. What am I even thinking? there's already a bit of a chain rule that we have to do. Combining that with a product rule, no thanks. The area of our triangle, well, I should say, yeah, area of our triangle, we're not differentiating yet. Area of our triangle as a function of its variable base is going to be, if I distribute the 1/2 b, we get 1/2 rb. I put the r in front because it's a constant, plus, oh, I guess we have a product rule anyway. No, not really. B times square root of r squared minus 1/4 b squared. It doesn't have to be a product rule because I can multiply the b into the square root and just do a simple chain rule. Yeah, b is the square root of b squared. Square root of b squared times the square root of the other stuff. You can multiply the insides of the square roots just fine. 1/2 rb plus square root of, it's going to be b squared r squared, or I should call it r squared b squared. Put the constant in front. Minus 1/4. It used to be b squared, multiply it by another b squared, now it's b to the 4th. Okay, perfect. Now we can differentiate with minimal troubles. So a prime of b is equal to a prime of b is equal to, we've got 1/2 r for the 1/2 rb part, plus the derivative of a square root is 1/2 times that square root. Like I said earlier, way earlier, the square root function is a function you should have seen enough times by this point that you can do this automatically. It will save you so much time. Master this. So derivative of a square root is 1/2 times that square root, and then because of chain rule, times the derivative of what's under the root. So times derivative of r squared b squared, derivative of b squared is 2b, so that's going to be 2r squared b minus derivative of 1/4 b to the 4th is, well, the 4 and the 1/4 cancel out, so you're just left with b cubed. All right, and this we need to set equal to 0. This we need to set equal to 0 to find the optimizing value of b. Alrighty, let's see what we've got. So if let's see. So I can factor out actually, I can multiply the whole thing. Yeah, hold on. Before I do that, let me copy it over. So we've got 1/2 r plus, to condense it a little bit, I'm going to write this stuff in the numerator. So 2r squared b, 2r squared b minus b cubed over 2 square root of, it was r squared b squared minus 1/4 b to the 4th. Okay, so that's our rewrite done. and, well, set that equal to 0. Now multiply by 2, and by 2. 0 times 2 is still 0, but at least we get rid of that noise. I would also want to multiply by this whole square root expression so we can clean it up a bit. So, well, do I want to do that? Let's subtract the r and then multiply. Yeah, let's do that first. I'm going to subtract the r over to that side, so we've got 2r squared b minus b cubed over square root of r squared b squared minus 1/4 b to the 4th equals negative r, and then multiply by that square root. And do I want to square both sides? Oh, decisions, decisions. We'll see. So we get, if I multiply by the denominator, we get 2r squared b minus b cubed equals negative r times the square root of r squared b squared minus 1/4 b to the 4th. And now, moment of truth. To square or not to square? That is the question. Well, I mean, I have to isolate the b's, so what choice do I have? Yeah, I guess I'm gonna have to square. Okay. I feel like there's an easier way of doing this that I'm just completely missing. This one is simple enough to do mentally. It's going to be, well, if I square, the negative is gone. Negative r times negative r is just positive r squared. So that takes care of our negative. And then times the square root just gets undone. So we've got r squared b squared minus 1/4 b to the 4th. Yeah, I don't see how this one's going to be solved all that easily. I feel like I may have messed up somewhere at some point, or I just missed some sort of simplification I could do. Anyway, if I FOIL this, I get 4r to the 4th b squared minus 2 times both of these. So that's going to be 4r squared b to the 4th plus b to the 6th equals, I guess I can distribute the r squared, so I get r to the 4th b squared minus 1/4 b to the 4th. Oh, actually, no, not too bad. It's actually a quadratic in disguise. Okay, yeah, we can do this. This is doable. Messy, but doable. So let's combine like terms all on one side. I'll do left side. So first of all, I want to rewrite the left side with b to the 6th first. And then minus 4. Yeah, let's rewrite the left-hand side before we move anything around. It's just easier to stay organized that way. Again, try not to mentally tax yourself too much. Try not to hold too many things in your head all at once, or else your chances of making a mistake rise dramatically. Rise dramatically? Rise dramatically. Are raised dramatically. I can English. This is why I'm not your English tutor. R to the fourth b squared minus 1/4 b to the fourth. Not written too well, but it'll have to do. Now then, I can subtract r to the fourth b squared on both sides, and actually that works out nicely. I've got 4r to the fourth b squared minus 1r to the fourth b squared, so now that's 3r to the fourth b squared. Okay, and add 1/4 b to the fourth. That one is going to be a bit messier. So I still have my b to the 6, and then I've got my, let's see, it's going to be plus, and then negative 4r squared plus 1/4, all that times b to the fourth, and then plus your 3r to the fourth b squared equals 0. Let me rewrite that so that it looks nicer. Let me rewrite that. So we've got b to the 6 plus negative 4r squared plus 1/4 b to the 4 plus 3r to the fourth b squared, and that all equals 0. This is a quadratic in disguise because if you, for example, say u equals b squared, then your, actually, wait, no, is it? Well, I can factor a b squared out of it. So that's one thing I should do first before I continue with this line of reasoning. I can factor out a b squared. So we're left with b to the 4 plus negative 4r squared plus 1/4 b squared plus 3r to the fourth. And then if I think of b squared as being a u, then b to the fourth is b squared squared, or u squared. So you've got u squared and u and a constant term. So yeah, that's a quadratic. I don't think we're going to be able to solve this by just factoring. I don't think so, but let's look at it and see if there's anything we can do. Multiply two things to get 3r to the fourth such that they add up to negative 4r squared plus 1/4. Yeah, right. We're not gonna figure this one out by factoring. It's quadratic formula time. This, I don't think, would show up on the AP exam because of how time-consuming this whole process is going to be. But yeah, we can go ahead and solve for, well, first of all, I want to rewrite it as 0 equals, I'll keep that factored out b squared as a b squared, but the rest I'm going to write as u squared plus negative 4r squared plus 1/4 all times u, not b, plus 3r to the 4. And I don't even have enough room to draw the closing parenthesis. Well, just barely. Yeah, that's not even readable. I should probably continue this on another page. Yeah, at this point I have to, because quadratic formula, this is going to be quite the royal mess. Oh goodness. So u equals that whole thing squared, or no, negative that whole thing. So negative of negative 4r squared plus a fourth plus or minus the square root of that whole thing squared minus 4 times, what's our a and what's our c? Our a is 1 and our c is 3r to the 4th. All over 2a, so 2 times 1. So that's our u, which is our b squared. So once you get this whole thing, you have to then take the square root of that, and that will be your optimal b. And of course, you have to check for, realisticness. Whatever your b value is, it can't be negative, right? The length of the base cannot be negative. So if the plus version gives you a positive and the minus version gives you a negative, eliminate the negative one. It's not correct. Only one of the two options will be right, I imagine. But I think I'm pretty much done with this problem at this point. I think I've done the main part. I think the rest you can take over from there if you're interested. But yeah, this one, unless I'm missing some sort of big simplification, there's no way you're expected to do this on an exam. This would work as like a homework problem because time wouldn't be a restriction on you, but on a test, no way. Let me go fix our lighting a little bit. There we go. I don't know if that looks better on screen, but it does look better for me. I think on screen it won't make much of a difference because there's already I might be mistaken, but I'm pretty sure OBS already compensates for lighting somewhat. But I guess I'll just have to look at the video and see afterwards. I'll have to see what the footage looks like. Yeah, it's just exhausting is all. Is there anything else I want to say about this before closing the door on it? So yeah, you do the plus option, you do the minus option with your quadratic formula, you figure out which one is actually going to give you a positive value, you get your b in terms of r, and once you have that b, you can plug it into your original area function. Well, actually, we would want to plug it into this version of the area function, which is written in terms of b. Whatever that b value is, you plug it in, you get an expression purely made of r, and that will be your optimal area in terms of r, a constant which we were just given to work with. I still feel like there's an easier solution that I'm missing. Maybe one of you will catch it, but right now I'm not seeing it. Or maybe it doesn't exist and it really is just as long and treacherous as it has been for the past however long I've been doing this one. Okay, let me see. I think we are actually at a pretty good point for stopping. Well, no, I want to go back to linear approximation and differentials, and then I think that's where I will wrap up for today, and we'll cover some other calculus topics in a separate stream some other day. So let's see, linear approximation and differentials. What do I want to say about linear approximation? It's the idea of it really isn't that hard, and I see this green marker is as good as dead. Let's trash it. And replace it with a new green. There we go. Let's see. So what do I want to say about linear approximation and differentials? Really just understanding the idea of linearization and differentials. If you can understand the idea, it'll help you know what to do when you get the problems. It's not really all that hard. It's just teachers don't really go over the intuition behind it, is what I find. So that's kind of what I want to do, especially for differentials. Teachers tend to focus on linearization more than they do on differentials. So let's see. I mean, you can linearize if you know how to get the slope of your tangent line and use it to write the equation of a line, which I would assume at this late in the game you know how to do. You don't get into calculus without knowing how to write the equation of a line, and you don't make it this far into calculus without knowing how to get the slope of a tangent line. So let's say let's go with the square root function, for example. Let's go with the square root function. And I'll do it in pink. So square root function looks like this. And suppose you didn't have a calculator handy, but you needed a rough estimate of, I don't know, the square root of let's say 4.2. You needed a rough estimate of it, and you didn't want to just round it to 2 because that's too rough of an estimate, but you need something a little bit better than that, but not too much. You don't need anything too precise. Let's suppose that was the scenario you were dealing with. You know it's somewhere close to 2, so let's say, where's my 1, 1 here? I guess I will put it, yeah, that looks good. So that's 1, whoops, 1, not 2. So square root of 1 is, oh, wait, no. If I do that, then I don't have a 2. Okay, never mind. Okay, I'm going to say this is where my x equals 4 is, yeah, I'm going to say that's where my x equals 4. And, well, forget about being true to scale. Even when I try, I just get screwed over by my drawings. No scaled graph today. Okay, so at 4, you get a y value of 2. For x equals 4, you get y equals 2. This is not drawn to scale. Just convince yourself that this is 4, 2 that we're looking at right here. Okay, 4.2 isn't too far off from 4. If this is, let's see, that's 2, that's 1, 3, 5 would be there. So 4.2 would be somewhere around here. 4.2 would be somewhere around there. So if I were to draw the tangent line, at x equals 4 for my square root of x function, you'll notice that yes, the tangent line is above the actual square root of 4.2. It is above that point, but it's not that far above, so you could get away with it. And as you can also see, the further away you get from 4, the further off you get. So I would not use this tangent line to approximate the value of the square root of, let's see, there's 4, 5, 6, 7, 8. So I would not use this tangent line to approximate the square root of 8, for example. Right? That gap is too big. That's your error right there. Error is way too large. Not worth it. You'd be better off anchoring at a different point using a different tangent line that's closer to this point so that you don't have as much error. So in order to get square root of 4.2, we can get away with using this tangent line. It'll give us a pretty decent estimate. And yeah, that's really all there is to it. Instead of actually finding f of 4.2, where f of x is square root of x, instead of finding f of 4.2, we can say f of 4.2 approximately equals, let's say that the equation of this line is g of x. Let's say that the equation of this line is g of x, so it's approximately equal to g of 4.2, whatever 4.2 gives you on the line. And that's all there is to it. You're just literally substituting whatever function you're given, polynomial, radical, exponential, whatever, with a simple linear equation that doesn't give you the exact values, but gives you values that are close enough if you anchor at the correct point. If I anchor at 4, if I get my tangent line for when x equals 4, then it's close enough to 4.2 where it'll work. For 8, I would probably want to anchor at, say, 9. 9 is a good choice because, 1, it's close to 8, and also I know its square root is 3. So anchoring at 9 and getting the tangent line there, you can even barely see that the tangent line is above whatever the square root of 8 is. So anchoring at 9 would work really well if you're trying to approximate the square root of 8. And yeah, I think that's all I wanted to say when it comes to linearization. It's called linearization because you're taking a function which is typically a nonlinear function, and you're replacing it with a linear function. You're practically making it linear, at least for a short range, around a certain anchor point, treating it as if it's linear, making it into a linear function. That's why it's called linear approximation. Sometimes it's easier to wrap your head around a concept when you understand why it's named the way it's named. Which is why I like to kind of dig into the meanings of the names of things in whatever I teach, whenever I can. I'm still sometimes looking at concepts that I never really thought about. Why is it called this? Why is it called that? But then one day, after seeing it a ton of times, the thought occurs to me, why is it called that? And then I kind of just break down the name and I go, oh, actually that name makes sense. But now I'm just rambling. Anyway, so that's for linearization. I assume you already know how to do it, so I don't think I'm gonna carry on with this. Yeah, get the slope of the tangent line, write the equation of the line, plug in 4.2 into the equation of the line. There's your approximation. Calculate square root of 4.2 on your calculator and compare the difference. That's your error. You can calculate your percent error by taking the error divided by the actual value times 100% if you want. All that good stuff. You can, if you've forgotten those, they're easy enough to pick up. Just grab your book. If you don't have a book, then use one of the free books on OpenStax for calculus. OpenStax, if you haven't heard of it, just Google it. It's spelled like this with an X. They have some free calculus textbooks you can use. And yeah, just grab a book, practice a couple problems. You'll quickly get the hang of it. It's not like it's hard to do. It's just a lot of people kind of go through the motions without understanding the concept behind it. And I find that helping people understand the concept behind it helps them actually remember what to do, even if it's long since they last had to do it. Okay, so what's the deal with differentials then? What's the deal with differentials? Differentials are just an alternative approach. Differentials are just an alternative approach to really the same kind of problem. Differentials are an alternative approach to what's really the same kind of problem. If you, again, say you want to approximate the value of square root of 4.2, instead of getting a, well, actually, I don't want to do it this way. Differentials make more sense as an application. Differentials make more sense when you do them in application problems rather than these. Well, let's do this one first, and then hopefully that'll clarify what I mean. So, with differentials, what you're trying to approximate is not f of x. What you're trying to approximate is the change in f of x. Well, I shouldn't say that either. What you're trying to approximate is delta y. So you have your, let me draw another copy of this square root function. Maybe this time a more zoomed in version. Oh, who am I kidding? I'm not going to be able to do that. I'll make it a little bigger. Let's say that's where you have your x equals 4. Let's say that's 2. Again, my scaling is off, I know, but just take it for what it is. Take it at face value. Actually, wouldn't that be the opposite of taking it at face value? Whatever, you know what I mean. So you get your tangent line just like before. And and let's say 4.2 is... I want to actually put it further out. Let's say you wanted to approximate here. Maybe not 4.2. Let's pretend this is 4.2. I know now my scaling is starting to look nonsensical, but I need enough space to actually illustrate what differentials are doing. So with differentials, you've got a delta x, the gap between your what I like to call the anchor point and the place where you're actually trying to get the value. So you've got your delta x, but then you've also got your delta y. So if I draw this triangle here, you've got your actually, let's see, which of these would I say is delta y? I would say this is delta y. This is the actual difference between square root of 4.2 and square root of 4. Right? That's delta y. So what you're doing is you're approximating delta y by saying delta y approximately equals this thing right here, this gap between square root of 4 and whatever the line gives you. This gap right here, which we don't call delta y, we call it dy. We call that dy. And then the delta x, we have another value that is related to it, which we just call dx, which just so happens to be equal to delta x. So dx, delta x, they're equal to each other because that's just how we frame the problem. And dy is the approximation we use to delta y. So we say delta y, the true value, is approximately equal to dy, the approximated difference between f of 4.2 and f of 4. So that's what differentials are about. This kind of seems pointless when you look at the linear version of this problem, the problem where you just use a straight line to approximate a function, but it makes more sense when you're doing like geometric problems or other application problems, because right now this dy really, it's not doing anything too different from what you would be doing here. It's here you have g of x, which is going to be in slope-intercept form, and then this dy just makes it so that you're doing things in point-slope form instead. So you're still using linear equations all the same, so it kind of feels like, what's the point in having these two different things if they achieve the same result? Right? Your g of x here, you can write your g of x as being some sort of slope times x plus some sort of intercept. But your dy, on the other hand, well, actually, now I think it might be worthwhile to work it out so I can clearly illustrate the lack of difference there is between these two approaches. So, yeah, let's go ahead and actually do this. So if I want the slope is the derivative, so f prime of x equals 1 over 2 square root of x. F prime of 4 is 1 over 2 square root of 4. Square root of 4 is 2. 1 over 2 times 2 is 1/4. So f prime of 4 equals 1/4. That's our slope. Okay, so if I write the equation, it's at 0.4, 2, so I've got y minus 4 equals 1/4 times x minus 2, and I can distribute the 1/4 and add the 4, so I get y minus 4 equals 1/4 x minus 1/4 times 2 is 1/2. Whoops, 1/4 x minus 1/2. And add 4 to the 1/2, so that's 8/2 plus minus 1/2 is 7/2. So y equals 1/4 x plus 7/2. So this is your g of x. And then to get g of 4.2, your g of 4.2 is just 1/4 times 4.2 plus 7/2. Okay, what about the differentials approach? With the differentials approach, you're saying that your delta y approximately equals dy, and your dy is going to be still 1/4, except we would write it as 1/4 dx. So if you write y equals square root of x, then dy equals 1/2 root x dx, and for x equals 4, you get a 1/4 there. So delta y approximately equals dy, which equals 1/4 dx. Okay, so this dy is going to be the y at 4.2, well, the approximated y at 4.2, so y minus y minus 2 equals 1/4 dx, dx being 4.2 minus 4, right? The gap between 4 and 4.2, that's what our dx is. It's just delta x. Oh, wait a minute. It's the exact same thing we had before. Come to think of it, no, it's not, because what did I do wrong? I copied wrong. This is I had the 2 and 4 reversed here. This should be a 2, that should be a 4. Okay, my bad. So that should be a 2, that should have been a 4, 1/4 of 4, that should have been a 1. Oh great, I'm screwing up all over the place today, aren't I? In which case a 1 plus a 2, this would have been a 3. So 1/4 of 4.2 plus 3, yeah. That's what it would have been. Oh well. So anyway, the point is, you see there's no difference, because it's still y minus 2 equals, it's still 1/4 x minus 4. In this version, you plug in 4.2 for x afterwards, whereas in this version, you plugged in 4.2 earlier. And that's all there is to it at first, it seems. But where you can truly start to appreciate the power of this is in more applied problems. So let's take a look at an example that makes more sense to do with differentials rather than linearization. Almost tore a page there. That would not have been good. Let me see if I can find something that works here. Okay, here's one. It says the edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1 centimeters. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume of the cube and the surface area of the cube. I'm just going to do it for volume. I'm just going to do it for volume. And then we will wrap up with, well, after this, there's one more thing I want to do, and then we'll wrap up for today. So we've got a cube. And we've measured its side to be 30 centimeters, but we could be off by as much as 0.1, did I say meters? 30 centimeters, but we could be off by as much as 0.1 centimeters. So maybe the actual cube is 29.9 centimeters to a side. So I'll draw an exaggeratedly smaller cube. Clearly not to scale, but that's kind of the point, is exaggeration. Maybe it's actually 29.9 centimeters to a side, or maybe it's 30.1. The error could be in either direction. Again, I'm going to draw an exaggerated version. This one is going to be exaggeratedly large, so large that apparently I can't fit it on the paper. Maybe it's 30.1 centimeters, or maybe it's anything between these two extremes. We don't know for sure. We're pretty sure it's 30, but we could be off by as much as 0.1 centimeters in measuring its side length. And that applies to all of its sides, by the way. So if we're off in measuring the side length, then we will be off in calculating the volume and surface area based off of that side length. Here's where differentials are much more valuable than linearization. So volume of a cube is equal to side length cubed, right? And if I differentiate here, if I take the differentials approach, derivative of v is just 1 dv. Derivative of s cubed is 3s squared ds. This is kind of like the differentiation you do for when you do u substitution with integrals, so this shouldn't weird you out too much. Well, maybe it would have weirded you out back when you hadn't done any integrals before. But yeah, dv equals 3s squared ds. So obviously we're not measuring the actual error here, but there's an approximate error. So delta s and ds we treat as being the same. It's equal to 0.1 centimeters. That's how far off you could be. The s that we're going to plug in after differentiation, just like with related rates problems, you plug in after you differentiate, not before. Let's see, so 0.1 centimeters, s is going to be 30 centimeters. That's what we think the actual value is. We could be off by as much as 0.1 centimeters. And now the approximate delta v, not the actual delta v, the approximate delta v is 3s squared ds. Actually, what I should say before that, the approximate delta v is equal to dv, which is 3s squared ds. So we estimate, it's still an estimate, but it's better than nothing, Our estimated error in calculating the volume is 3 times 30 squared times 0.1. So our approximate error in volume, 3 times 30 squared times 0.1. I should be able to do this without a calculator. Oh well, calculator was already brought out anyway. 270 cubic centimeters. Now, we can calculate the real maximum error if we just assume the extreme cases, 30.1 and 29.9, and just calculate 30.1 cubed, 29.9 cubed, and 30 cubed and compare them, we can get the actual delta V values. And we will be able to see that the approximate error isn't going to be too far off from the actual error, because our ds is pretty small relative to s. The smaller your ds is compared to s, the more your dv, the better your dv approximates your delta v. That's kind of how this works. So let's see, 270 cubic centimeters. And I guess here I should kind of illustrate what this is even doing in the first place and why this is a valid approximation method. What is it really doing? So what it's doing is it's calculating the delta V. It's kind of like trimming. It's trimming or adding, depending on whether you think the error is an overestimate or underestimate. I'm going to say overestimate for now. So if it's an overestimate and the actual volume is smaller, then what you're really doing with the dV is you're trimming off 0.1 centimeters. It's approximating what happens when you trim off 0.1 centimeters from each of the sides. Well, no, this, let me think. How would I illustrate it for this one? Because it's not going to be a perfect trim. There's going to be some difference. There's a problem in my mind right now that I can think of that would be a much better illustration of this, and I actually did a video on it. It's an unlisted video, so you won't see it unless I make it public or share the link. But the problem with that one is it's a multi-variable calculus problem involving differentials. It would be so much easier to explain it with that one, though. Let me think. Is there a way I can do it with this cube problem? Give me a few minutes here. Okay, yeah, I've got it. So what it does is it calculates I had it and I lost it. Oh goodness. So you're trimming off 0.1 centimeters worth from everywhere, and okay, I think I've got it back now. It's coming back to me. Okay, so yeah, you're trimming off 0.1 centimeters from every side, and what the 3s squared ds is calculating is It's calculating the volume lost from, say, trimming off this piece, and that piece, and that piece, and that piece. But the reason that, did I say the DS? The DV. The DV is calculating the volume lost from losing those sections of volume. But what it's not taking into account, and the reason why it's an approximation of the error rather than the actual error, it's not taking into account these corners over here. It's not taking these corners into account. These corners require something a little bit more sophisticated, because these corners are volume errors that arise from the error in multiple sides at once, and this dV reduced by 0.1 centimeters, or increased if that's the way you prefer to go. So yeah, those little corner areas, those intersection corner areas, those aren't being taken into account by this dV. Now, that's not entirely the whole truth, but it's approximately what's happening. So it gives you some idea of why this dV isn't quite the same as the actual delta V value, but still it's a pretty decent approximation nonetheless, because if your ds isn't, if your delta S, your ds, isn't that different from your S, then these corners that are not being taken into account, they're small enough to be negligible. They're small enough to be negligible. So yeah, that's the basic idea behind what dV is actually calculating. It's not calculating, you know, a new volume and subtracting it from the original volume. What it's doing is it's starting from the original volume and adding or removing to it. In my illustration, removing these darker sections. Actually, I don't know if you can tell anymore what's darker, because this is a pretty dark shade of green. Does it show that well on the computer? Not really. It all looks like a blur to me. I probably should have used different colors. But yeah, that's what it's doing. Let me see. So yeah, a dV of 270 cubic centimeters, that's basically the volume of those dark pieces, not taking those corners into account. If you took all of them from all around the cube, they'd have a volume of about 270 cubic centimeters added or removed. Now then, it was asking for a couple of things. It said use differentials to estimate the maximum possible error. So that's that. Sometimes called the absolute error. The relative error. Relative error is well, actual relative error is the actual delta V over the V, but in our case we're approximating it, so we're going to use dV over V. And then the percent error is take your relative error times 100% and convert it to a percentage. That's all it is. So 270 cubic centimeters. Let's compare that to V. So our V is going to be 30 cubed, which is 2,700. No, 27,000, right? Yeah, 3 cubed times 10 cubed. 27 times 1,000. Yeah, 27,000 cubic centimeters. So 270 over 27,000 is 1 over 100, it looks like. So our relative error equals 270 over 27,000 equals 1 over 100, and then, or equals 0.01, and then our percent error, our approximate percent error anyway, I should say approximately equals, times 100%, so 1%. Now, as for our actual error, and they said maximum error, not minimum error, so I would calculate the two volumes, subtract the 27,000 from them, and see which one is bigger. I already know that the bigger cube is going to give us the bigger error, so I'm just going to go ahead and do that. 30.1 cubed minus 30 cubed gives me 270.901. So max absolute error, or just max error, is 270.901. So our actual relative error is 270.901 over 27,000, which is going to be a little more than 0.01, which is going to give you a little more than 1%. But still, it's not too far off, as we have now confirmed a couple of times. Well, actually, we just confirmed it now, but we were justifying it a couple of times earlier. Okay, so there's a simple walk through differentials. Now let's take a look at using either approach, the linearization approach or the differentials approach, to estimate given numbers. This tends to trip students up because they don't know what to do. It's one of those, once you see how simple it is, you'll feel silly, but it's just when it's thrown at you out of context and you have no ideas, that's where it tends to trip you up. So it says, approximate the given number. 1.999 to the fourth power. They want you to approximate that. And that's it. So I haven't given you a function. You have to come up with the function for yourself. And that's what tends to trip people up so much with these. The function, in my case, is going to be x to the fourth. That works perfectly. So we've got x to the fourth is going to be our f of x. So f prime of x is going to be 4x cubed. And from there, so we can approximate, let's anchor at x equals 2, because 2 is really close to 1.999. So let's do f prime of 2. F prime of 2 equals 4 times 2 cubed, 4 times 8, which is 32. Okay, perfect. So we can use that. We can either do linearization or differentials. I'm feeling like differentials today. So dy equals 4x cubed dx, which in our case is going to be dy equals 32 dx. Okay, what's our dx? It depends on where we anchored. We're anchoring at 2, so our dx is the difference between 2 and 1.999. So our dx is going to be 0.001. .001. So that gives us our dy, which is going to be 0.032. Okay, our dy is 0.032, and We anchored above 1.999, right? We anchored to the right of 1.999. So, actually, I guess, would that make our dx negative then? Yeah, it should have been negative. Yeah, my bad. Because dx is defined as the x value you want minus the x value you're anchored at. So 1.999 minus 2. Okay, so negative 0.032. And that dy is supposed to approximate the difference between, that's supposed to be 1.999 to the 4 minus, we anchored at 2 to the 4. That approximately equals negative 0.032. So 1.999 to the 4 approximately equals, what's 2 to the 4? 16. So 16, if we add it to the right-hand side, minus 0.032, which is 15.968. And there we go. That's how these work. Let's see. We have, what else do we have? We've got cube root of 1001 is another one. Approximate cube root of 1001. Actually, it might be easier to reverse engineer this and rewrite it as a cubed function. Actually, No, let's not do that. No, let's not do that. Okay, so this suggests that we use f of x equals f of x equals, let's see, the cube root of x, which of course we can rewrite as x to the 1/3. F prime of x is 1/3 x to the negative 2/3, which can be rewritten as 1/3 cube root of x squared. Okay. And I think I'm still going to use the differentials approach. So we want to anchor at cube root of 1000 because I know the cube root of 1000 easily. That's 1. And 2, more importantly, it's close to 1001. The closer you are, the better your approximation. So let's see. We have f prime of 1000. Well, let's see. So dy equals 1/3 cube root of 1000 squared dx. Cube root of 1000 is 10, and 10 squared is 100, so 1/300 equals 1/300 dx. Okay, and from there, let's see, so we anchored to the left of 1001, so yeah, it's a plus. Our dx is plus 1, right? Our dx, our actual value 1001 minus our anchor value 1000 actual value minus anchor value, dx equals positive 1. We're trying to approximate for something that's 1 to the right of our anchor. So yeah, times a dx of 1. So dy equals 1 over 300 times positive 1, which is 1 over 300. So that means we add 1 over 300 to the cube root of 1,000. So cube root of 1,000, of course, is 10. So where do I even write this? I don't want to bring out a whole new sheet for just one last line. We've got some space over here. Let's use it. So cube root of 1001 minus cube root of 1,000, which is what dy approximates, approximately equals dy, which is 1 over 300. Add cube root of 1,000 to both sides. Cube root of 1001 approximately equals whatever cube root of 1,000 plus 1 over 300 is. Cube root of 1,000, of course, is 10 plus 1 over 300. I imagine that's calculator work, which, I mean, if you're using a calculator, then that kind of defeats the point. Why approximate if you have the calculator? This is... I don't know. Well, I mean, I guess you could... Okay, we can write it as 3,000 over 300, so you could rewrite it as 3,001 over 300 to keep it pure and non-calculator. But yeah, that's as far as that goes. And that's also as far as we go for today. Yeah, I definitely want to do more of these, and this time I'm starting earlier as opposed to last year where I started in the last week before the AP exams. This time I'm starting earlier, so I have a bit more leeway, but I don't want to relax too much. I don't want to be, you know, lulled into that false sense of security just because I'm starting with more time. I want to do these more frequently. This was the first time I tried doing a scheduled live stream on YouTube. I wanted to experiment and see how scheduling a live stream works, and it looks nice. I mean, I was able to figure it out. It was a new experience, and, you know, increasing your YouTube skill is not a bad thing. Not a bad thing at all. So, yeah. Hopefully this has been helpful. I will continue with other topics, hopefully, unless I get sick or something, or, you know, electricity goes out or any other unpreventable disaster occurs. But my goal is to do more of this, and hopefully between what I'll be doing for this year and what I have done last year, there's enough review material out there for you. And yeah, anything else I want to say? Not anything that I can think of. Anyway, take care. Enjoy your last 2 weeks before AP exams, unless you're actually taking one of those delayed exams, because they have a different weird exam schedule this year. Some of the AP exams won't occur until like June, so that's interesting. So know when your particular AP exam is, so that you know whether or not you actually have the time, and good luck with your preparation, and I'll probably see you in the next stream. So yeah, that's it. Stream over.